I'm into the sonic bubble that is the Cisco U Theater today. We are ready to go. Everybody attend the keynote, go through it, good stuff. I was up here rehearsing all morning, so I didn't get a chance. I'll catch the recording and see all the excellent news that was out there. But today, here in the Cisco U Theater, we are going to talk about the new skills, same packets, how we can win as a network engineer in the AI age. My name is Hank Preston. I'm a distinguished architect here and Learn with Cisco, and I'm excited to be on this journey to artificial intelligence with each and every one of you, because it totally is a journey. And it's a journey that I'm trying to navigate as best I can, right? Every day seems like it's some new alert that comes out, a new tool, some new terminology that I've got to figure out. And it seems like everybody else knows this already, right? Or is it just me, right? I feel like I have no idea what's going on because everybody else has it figured out, right? You guys have it figured out? No? Okay. If anybody does, feel free to come up. You can present. I'll sit in the audience and learn something new. But I didn't think so because we're in the same boat. In today's session, we're going to go through a handful of topics. We're going to start out with this introduction, which I've already gotten into, and then this will end fairly quickly, and we'll get into some AI basics and fundamentals. It's almost like with artificial intelligence, we're going back to the early days of our CCNA studies, right? There's new words we have to understand. What is an LLM, right? What is a prompt, right? What is this hallucination, right? I used to think that was a great thing, but now we're being told that hallucinating is a bad thing. So we'll hit some fundamentals. And then we'll start to dive into what AI is going to mean for us as network engineers in our day job, the things that we do. And when I look at it, and I consider how I'm using AI and thinking about AI, I've put it into these kind of three different hats, three different approaches we'll go through AI, and we'll talk about all of those. And then we'll spend a little bit of time showing some specific use cases, ways that we can actually use AI today as part of our job to take away some of the tasks, do some of the things that we're after. And those types of use cases evolve kind of every 6 months. Like there's new ideas, new things that we can do with AI. And that's part of this growth, that's part of the journey. As the technologies, the skills, the services become better, we'll have more and more use cases we can go after. Then we're going to dive into the skills themselves. What is it that we need to learn? What are the things we need to approach so that we can be effective network engineers in this artificial intelligence age where we're being asked to embrace, right? I imagine you're all being asked. I'm totally being asked to embrace AI, right? Everybody seems to think if I put AI in my pocket, I can do 10 times the work. I haven't gotten to that metric yet, but I'm trying to get there as fast as I can. So what skills do we need? And then we'll end with a little bit about what we can do, what we're doing here and Learn with Cisco to help all of you learn these AI skills and be successful. So this movement into artificial intelligence is not the first time that we've had to adapt and evolve as network engineers. If you've been in this area as long as I have, you've seen us move from early days of networking where the focus was pretty simple, right? All we had to worry about was some VLANs, make sure that we had backup links, Spanning Tree took care of the heavy lifting for us, and things were pretty smooth. Because frankly, in the early days, the network was just a convenience. It made it easier for people to print because they didn't have to have a printer in their office. And then we kind of evolved into the dot-com era and the internet, where the network and being connected to the network was really critical to the business. And we started to be seen as a critical utility for our offices. We had to understand how WAN design worked and partner with service providers so that we could be effective and connect all of our offices together. Learn about routing protocols, right? The IPv6 started to come in as the internet became bigger and bigger and more hosts were connected. After a while, we hit what I refer to as the architectural renaissance. We'd been doing the same thing in networking for a long time, and we needed this space. We had to be shooken up a little bit. And so this is when software-defined networking started to really get the early days, right? Anybody remember OpenFlow, the concept where we're going to have white box switches and controllers running in the cloud, and we didn't need this distributed intelligence anymore, right? Elements of that made sense, but a lot of that we kind of experimented. We looked at it and said, okay, maybe it's not all here to stay. But we did get a lot of really good ideas in the architectural renaissance, which then moved us into network automation. We took things like software-defined networking and APIs, and we realized as network engineers, some of us had to learn how to code in Python. Any Python developers out there, scripters? Right? Yeah. You've used APIs. You've embraced tools like Ansible and Terraform. We're starting to move down paths of source of truth. Like the network automation age was really fantastic. It gave us kind of a nice transition. And I'll be honest, I was really content a few years ago to think that I was gonna end my career in the network automation age because I felt really comfortable there. And I was pretty good at network automation. I knew what I was talking about. And then before we knew it, we hit 2022 or November of 2022 and ChatGPT was released. And oh my God, we end up in the artificial intelligence age. And now I'm back in school. I'm learning new things. I'm trying to figure out what LLMs really are, right? What's the difference between training and inference? New terms that I'd heard in the corner of my mind, but I didn't pay attention to, like Rockies came out and GPUs, right? I knew what a CPU was. The only thing I thought a GPU was good for was so my son can play Halo better, right? Now I've got to figure out, like, why do I have so many GPUs in my data center and where's all this power going to? So we're back at school. We're doing this together and it's going to be fantastic. Now, you've probably all heard the words that are out there. AI can do so much for us. So it's a fair question to ask, right? Do we even need to learn networking anymore? And I'll tell you, absolutely. We have to be fundamentally still learning those basics. We have to learn how networking works because time and time again, the research has shown that to be an effective user of artificial intelligence, you need to know the source material. You can't give AI tools to a novice and think that they're going to be able to perform at the expertise level. Right? As an example, I can go through and I can use AI and YouTube and these things, and I can figure out how to change the oil on my tractor, but I don't feel like I could use those same tools and then rock up into a surgery wing and figure out how to take somebody's appendix out. Right? I still need to learn the basic skills, and that's why learning networking is more critical than ever, because we're going to be expected to get to that level of expertise faster in the future. Because AI will allow us to do things faster and take away some of the time that we would spend on the fundamental basics. We have to be able to figure out, how do we learn networking? How do we learn it faster? Because we have to avoid trying to use it as a shortcut, right? AI is not a shortcut to expertise. We still need diligent practice. We need the hands-on skills. We need to know the fundamentals. We need to learn networking because the human network engineer still matters. Artificial intelligence is just a tool in our portfolio. It's no different than having PuTTY back in the day or having secure CRT. It's just another thing that we can leverage because we bring to network engineering something that artificial intelligence never will. We bring human ingenuity, right? We bring the ability to come up with creative, out-of-the-box thinking experiments that are there. Artificial intelligence is fantastic. Generative AI is awesome, but it is just a prediction engine to figure out, like, what is the most likely answer to a question or a prompt that comes in. We are going to bring with us that creative ideas. We will bring all of the context, the business history, the business priorities into the conversation and be able to use artificial intelligence effectively to get to those answers faster. And in the future, deploy the solutions even faster. But nothing's going to replace what we are going to offer the world as network engineers on that side. So if you're worried, right, is there a future where network engineers are no longer needed? I don't think so, because I've been more effective as a network engineer, but I still need to be the engineer for my organization. So hopefully that's made you all calm down a little bit, not so worried on that side. So let's learn a little bit about the basics and fundamentals of artificial intelligence. Now, I only have about 30 minutes here today, so we can't get through all the details, but I did want to kind of give a survey of some of the key terms and just level set what all these things mean. And we'll start out with artificial intelligence and machine learning, two terms that are often brought together, and they are definitely related, but they're different, right? Artificial intelligence is this area of study and research and technology where we're trying to build computer systems and programs that can simulate different elements of human intelligence, different elements of intelligence. And AI has been around for a really long time, right? If you've ever gone into Netflix or Amazon or Prime and had a recommendation pop up to say, hey, you watched this movie, this one might be good, or you read this book, maybe you'd consider this one. Or, hey, we've noticed that you're talking in your house an awful lot about interested in moving, so here's some real estate stuff that goes after. All of these predictions and recommendations, that's part of artificial intelligence that has been growing for decades and decades, and we've just taken that for granted, right? Generative AI is the new thing, right? Machine learning is a field, a portion of artificial intelligence that allows us to build the algorithms that allow machines to start to learn on their own, to build those patterns, recognize the connections, The early days of artificial intelligence was about kind of trying to hand code everything that we might consider that's out there. We would write them ourselves into big rule engines and try to just educate them directly. Machine learning was the innovation that allowed us to say, no, let's see if we can figure out how to let the algorithms learn themselves and build themselves up. And that made the artificial intelligence boom go so much faster. As I mentioned, generative AI is the new kid on the block in the AI world. There's classification, recommendations, computer vision, and generative AI. Generative is the keyword. Gen AI creates new novel things based on the training data that went into the building, the machine learning phase that was there. When you ask a generative AI system a prompt, what it begins to do is to try to figure out what is a reasonable or most reasonable answer to the question you asked, based on all of the connections, the patterns that are involved. And it can seem amazing what can come out of these systems, because the training that's gone into these generative AI LLMs has come off of so much data that it can make the connections in place. It can do things like translations. It can do things like QA your configurations that are out there. It can come up with ways to explain things in a different fashion to make it easier. And there really is a lot to just be impressed about what generative AI has brought to us in this AI field. Now, we haven't even stopped with generative AI, right? This came through, and then it started to open up new opportunities, new things that we might be able to go after, like Agentic AI. I imagine you've probably heard about that at Cisco Live already this week, because that's the new big thing that we're hoping for. And Agentic AI is this kind of journey that we're on. The grand vision of where we'll get to with Agentic AI is a world of autonomous AI agents that are part of our network engineering teams, where we build up the trust, the capabilities with these AI systems that we can allow them to kind of look at the network, understand what's going on, follow our instructions, and make decisions on their own to achieve the goals that we have set that are out there. Now, this doesn't take away the concepts around human in the loop or expert in the loop. It's going to be a portion where we start to onboard AI agents onto our teams. It's really not all that different than when we hire a new human engineer onto our team. We give them a few jobs up front. They learn how those things work. They build their skills. We build confidence that they know what they're doing, and then we give them a little bit more autonomy. We're going to be doing the same thing with these agentic AI systems, but in some cases that will come from the training, the services that are involved on that side. That's where we're trying to get to. Today, most of what agents are that you might build are a combination of some sort of a role and a persona, and then an LLM that will help you kind of do some specific task. You can build an agent today that says, okay, I just need you to look through this log data and tell me, is there anything that I should be worried about? Right? That's something that Agentic AI, building a simple agent today, can be really useful for. You can leverage tools that we can put into our AI agents' hands today to reach out into our systems and maybe run show commands across the entire network to collect data. Maybe you've got an agent that's tied into your source of truth, so you can kind of compare information from different locations. And so this Agentic AI world is how we're going to be able to actually bring in those AI agents into our team to do some of the work for us. Now, what powers each and every one of these AI technologies and concepts is the idea of a model, an LLM, a large language model. And the model is the actual computational structure that was created through all of the training information. At its base, the model is just a file, right, or a series of files that need to be run on a piece of software that allow you to actually send in an input that will be processed by the model through all of the parameters, the weights, the training data, and then come out the other side with a recommendation that seems likely or fits in with whatever it is that you asked on that side. The model is what powers. It's kind of the machinery that's in place, and it's all the inputs that are going to change the output from the model. You can take the exact same LLM, the exact same AI model. For example, here's the open source version of ChatGPT, OpenAI, released a few months ago. And you can take that model, and that model could become a network engineer on your team. That model could become a user that you wanted to kind of practice your skills with asking questions to figure out what's there. Or this exact same model could pretend to be a toddler, right? What matters about the model, or what matters about the results, is not just the model. It's what you're providing as the input, the instructions that are after. And that's a lot of the power and the flexibility that comes after it. What you send into a model is a prompt, right? Prompts are the input into a generative AI conversation. It might be a question. Can you explain the difference between a VPN or a layer 2 VPN and a layer 3 VPN? It might be a request. Hey, I'm practicing this presentation that I'm going to give. Can you act like an audience member for me and give me some questions that might be relevant to this presentation? The prompt shapes what's going to come out of the response that's there. The art of creating prompts that result in the best answer possible is what prompt engineering is about, right? The promise of AI, the promise of generative AI is that we don't have to kind of focus that much. We can just talk to the system like another human being, right? I like that promise, but the fact of the matter is we very quickly went into this idea to say, no, we need to train people on how to prompt engineer. Because to get the best results out of the AI systems is if you want to craft your prompts just right. You want to use this style of delimiters to indicate when you've got steps involved. If you want your answer in a certain framework, right? You want to provide templates that go after it. And so just like many of us had to learn how to correctly craft a Google search to find the page on the internet that we were after, prompt engineering is how we're going to learn how to create the prompts to get the answers out of the AI that we're after. It's no different than what we've done in the past. Now, one of the dangers that we hear a lot about with artificial intelligence is it's not always accurate, right? Does anybody still think that AI will always give you a 100% truthful answer? Absolutely not, because that's not what AI and LLMs were designed for. They were designed to give you an answer that sounds good. Right, which is really weird that we have put this much faith in a system that was designed to give you an answer that sounds good. And when you get an answer that sounds good but is not accurate, that is referred to as a hallucination. The LLM sat down and said, wouldn't it be great if this was true? And I'm going to tell you it's true. That's what hallucinations are. That's that opportunity where the AI algorithm went in and said, okay, I'm going to go this direction because this sounds pretty good and it can make things up. One of the skills we're going to talk about is the importance of being able to just kind of always have that critical thinking hat on, always be ready to question, always to be ready to kind of put the extra effort in to validate that the answer that comes out was truly accurate, which is why one of my favorite uses of AI is not necessarily to ask a question I don't know the answer to. It's to ask a question that I'm pretty sure I know the answer to. I just can't remember right now. Because those are the places where I can very quickly spot, yeah, that sounds right, and I can go into it. If you are using AI to get new information that you're not fully aware of, make sure you're checking the work. And there are strategies we can use with AI to make this easier. We'll talk about one of those in a minute in a demonstration. Now, Cisco has had a pretty good last couple of years with AI out there because the network is really critically important to how AI works at scale. There are two phases to use it to create in generative AI. There's a training phase where those little baby LLM models that don't know anything are flooded with petabyte after petabyte of data from the internet. And they build those relationships and weights and they start to understand what's out there. That training phase requires a very high bandwidth, low latency network that connects clusters of GPUs and hosts that are out there. So we're having the networks in our data centers are starting to be built because they have to have even faster bandwidth, 100, 400, 800 gig links, right? We have to be able to use new technologies like Rocky with RDMA and all of these new QoS capabilities to make sure that those GPU workloads, those training don't lose any data. So there's so much work we have to do in this space. So the network really is critical in order for AI to effectively work. Now, I promised a discussion of the three different ways that we're going to interact with AI as network engineers. And I've broken them up into these three buckets: users of AI, supervisors of AI, and builders of AI. Now, we all start at the first phase of users of AI. As a user of AI, you're going to kind of tackle and look at, how can I use AI in my day job, right? Can you check this configuration for me? Can you give me the answer to this? Somebody told me Hank was up on the stage and he mentioned the word inference, and I have no idea what that is. Can you tell me what inference is? Can you process this CSV file? Can you help me come up with some really interesting IP addresses to use for the host? These are all ways that we use AI. Now, as the agentic AI world comes along and our team is start to be made up of different AI agents, we will find ourselves being supervisors of AI tools. We will be selecting, we will be hiring the AI agents. We will be training them and assigning them tasks and jobs, evaluating the work that they do. That will be something that we start to do as a supervisor of AI tools. And then we also have to build AI infrastructure. We have to build these large data center networks that will allow the AI clusters to work effectively. We will have to connect all of these large hosts that are there. We may have to design and build some of the agentic workflows that will go in. So there's a builder of the AI elements that will come into this as well. And so each one of us will evolve our workloads through these different areas. So if you haven't really kind of embraced the user of AI tools, start here. This is the easiest way to get started with a lot of interesting possibilities. And so let's go into some of those right now. What are some of the use cases for network engineers around AI? Now, the first place we're going to start out with is just using AI to answer questions or help us with work that's there. Now, when I first started talking about AI for network engineers a couple of years ago, AI was kind of the LLMs were just in their box. But today, most AI tools have access to the internet. They can do web searches for you. And so you can go in and ask questions like, I'm preparing to upgrade my system from this version to the next version. Can you tell me any caveats that I should be aware of? What bugs were fixed in this release? Basically, you're offloading the effort to go find the release notes and read through them to an AI agent that can do some of that work for you. It's a really nice use case for AI. But again, check the work, look at what the resources were, where the citations came from, because that will help you on that side. Now, one of the other ways that you can avoid the dangers of hallucinations is by providing source material. So here's an example where I've uploaded all of the iOS XE configuration guides to my LLM, and it goes into a library that uses a technology called RAG. And here, now the answers that come out of this will be focused just on coming out of just the documentation I gave it. So when I ask a question, it searches the library to find the answer. Now the risk for hallucination isn't gone, but it's much less than if it was just using whatever data was in the trained model. So whenever you have an opportunity to provide source material, take advantage of that with your AI use cases. It vastly reduces the chance, doesn't go to zero, still check the work, but it vastly reduces the chance for hallucinations when you're after those types of areas. Now you can combine RAG here with a use case that I call my network reviewer, a network peer reviewer. Now, every one of us always loves to have the idea that I've got somebody to kind of look over my shoulder, check my work. If you're in a shop where you're the one person, one network engineering team, maybe you don't have someone to talk to. So maybe you would go to a Cisco partner, or you'd call Cisco TAC to review stuff. By combining good information with an AI tool, you can actually use AI to be that second set of eyes for you. You can upload configuration examples and templates and say, can you take a look at this and see what I might have missed? And it will process through it and point out things that you may not have considered. This is one of my favorite use cases, not to create configurations. Someday, maybe we'll get to that point, but I like to use it to review my configurations and tell me what I might not have considered. What might I have missed as I was making this evaluation that was in place? Okay. Really like this one, particularly when I combine this with good source material like configuration guides or CVDs, and I can push this into the AI models to take advantage of. Now, agentic AI, right? This is when the real power of agentic AI comes in when we can start to give the AI agents access to tools, right? Give it some hands, virtual hands and eyes that it can reach out to the network. And so in this example, I built an MCP server, which is a kind of a current de facto standard for building tools for our AI systems, that was written in Python, because I do most of my work in Python. And it provided the ability for an AI model to send show commands off to network devices. And for this example, I'm using CML for a small network. I'm using LM Studio as my AI tool because I want to make sure that it's secure and private. And then my code example that's on the side. And this gives me the ability to use my AI tool and say, okay, can you tell me what version of software is running on this particular device? The agentic AI combined with the tools says that my AI can go through and say, okay, let me take a look at this. And I think I'm going to use the send show command tool. And then it crafts that command, and it can actually use that ability to reach out into the real world and send a show command. And then, I missed it already, and then process what's in place. As we provide more and more access to tools and the ability to reach out into the real world, the questions we use our AI for can become more interesting. There's a host connected to switch 01 with this IP address. Can you use the ARP table from the router to determine the MAC address and then find the port on switch 1 that this MAC is attached to? Something I've had to do a ton of times as a worker. I can certainly do this myself, but I've used this example to show how with Agentic AI and the ability to put tools in, we can actually use this automation to give us that ability. And the tools will go through and fire off and kind of tackle all of these on their own. It's a really interesting way and kind of how the Agentic AI will make it more powerful, make us kind of be able to scale out a little bit. Now, I will say, like with most network automation, doing this one thing at a time is not faster. But imagine something like this where you wanted to do this across an entire network of hundreds of hosts or thousands of switches. This is where the AI and the Agentic AI will help. It's at the scale side of it more than anything. All right, let's move into some of the skills that are going to be really important for the AI-enabled network engineer. And I wanted to start with a couple of stats to say why you should be interested in the skills. We're seeing almost a 200% growth for AI-related skills in active job postings today. That means every organization is looking for engineers, no matter what the job is, that have the AI skills. And if you have them, you can demand an 18 to 47% higher salary. So it's valuable to learn these skills. And I'll give you a hint. The level of skills, like the expertise you need in AI to get some of this, is not super high, right? Because it's so early, just putting a little bit of effort in will go a long way. Some of the skills that you need to learn is I've broken into kind of two buckets. There are general skills that just everybody in the world needs to know to be effective users of AI. We need to have the critical thinking skills. We need to understand the fundamentals, prompt engineering. We need to know what data literacy is all about. Like, there's just some things that we just need to know to be effective kind of humans in a world where AI is everywhere, no matter what our job is. But on the networking side, right, AI is definitely going to affect network automation and software-defined networking. We're going to move AIOps into the NetDevOps world. We're going to see impacts with cloud and hardware and all of these focused areas. So there's different places that we have to focus in on these different AI skills. There's a robust set of things that we can learn. And so you're probably trying to figure out, okay, well, how can I learn all of this information? Well, thankfully, you can learn AI with Cisco, right? We're learning with Cisco, and we are focused. Everybody in our team right now is focused to help each and every one of you pick up the skills necessary to be effective users of AI in your job role. We have a robust portfolio and roadmap of training that has different areas of AI that can go in. All the ones in gray have already been released with hands-on tutorials or actual learning paths related to AI business skills and AI technical skills that are in place. If you want to focus in on areas around how the new UCS platforms with ACI work, or this the Splunk and AI operations, right? We've got lots of material that are constantly coming out. And many of these are being made available as free on Cisco U in tutorials or as part of our RevUp program. So if you're not already a Cisco U member, I highly encourage you to check that out, because this is constantly going to have new things being added for it. Now, I could go on and on and on about AI. Frankly, I've got 2 or 3 more sessions this week where I will continue to talk about AI, but we're coming to the end today in this session here in the theater. But I wanted to leave you with some links. You should be able to find these slides. Right, so taking a picture of this one is great, but the actual link information is in the Cisco Events app. If you go to your session files, and you should be able to find the slide deck from here. So you've got links that'll take you to different labs and resources on Cisco U to help you start using AI, supervising, or building AI. Try to collect them into those types of in those areas. So in closing, right, some of the key takeaways that I want each and every one of you to remember. AI is here, right? It's meant to empower you, not replace you. But to some extent, if that's going to be effective, it's up to you. Right? You have to learn how to bring AI in and be empowered. Don't avoid it. It's similar to what we had to do with network automation. Like, you just can't avoid these things. Right? Jump in 2 feet, learn how to make your job easier. And we are updating all of our certifications and training for the AI era to make all of you be successful, just like we helped you all become successful network engineers to this point. We're not going anywhere, and we'll be here together to build the network for the future. Now, it is a journey. I'm on it with all of you. I am certainly not an expert in this space. If you want to follow or if you've got questions, you want to follow along, my contact information, you can take a picture of this one if you want to find me. I'm pretty easy to locate, hapresto@cisco.com. I'm always eager to hear from folks on their journeys, help you on your way. And I'm trying to keep active up on blogs.cisco.com with my own journey, things that are out there for this area. All right, with that, I've come to the end of this session here in the Cisco U Theater, but there's plenty more going on here in the theater for the rest of the day, as well as elsewhere here at Cisco Live. I want to thank you all for coming, and please enjoy the rest of your time here in Melbourne. Thanks, everybody.
Cool. Okay. It'll be useful if you turn it on. How you all doing? It's been super cold in Melbourne for this time of the year, huh? I'm not sure if there are locals here, but what's up with that? Can you guys not hear me? Is it in and out or? Thumbs up if you guys can all hear me. Okay, good. I don't want to be talking to myself. Oh, your volume. Okay, so just adjust your volume. Climate change, right? That doesn't exist though. Okay, yeah, it's been freezing, man. I don't know. I'm not. I normally come here, sunshine, and it's beautiful. So, but anyway, let's get rolling on this. Thank you for joining me today. I'm Kareem Iskender. I'm a principal engineer with Learn with Cisco, and I am here to talk to you about integrating MCP and what MCP is in NetDevOps. We've been talking to you a lot about NetDevOps. If you've joined our journey in automation since day one of DevNet, we've always talked to you about building some CI/CD pipeline. So what we're going to do today is just going to give you a quick introduction of where we were and where we're headed. We're going to look at NetDevOps as we know it in general, and some of you might be very familiar with that topic. Might have seen actually some of the slides if you attended some of our old DevNet sessions. And then from there, we're going to look at how AI fits in our automation and what we build as network engineers. And for those who are not familiar with MCP, I'm going to talk to you about what MCP is, why it matters, and then I'm going to give you a really cool demo that's going to resonate really well with you with MCP and AI, with resources where you can take my demo and implement it on your end. Okay, so there's a lot of information. Let's make it interactive. If you have any questions, raise your hand. I'm happy to answer it, and we'll just go from there. Okay. So if you look at this slide here, we talked to you about NetDevOps. We said, hey, when you're building some automation, it's best to build some CI/CD pipeline that is gonna maybe allow you to basically push your automation script to GitHub, have some type of version control, and automatically update configuration, maybe leveraging Ansible for this. Or, this is back from 2017. We talked about maybe you need to test your configuration before you apply it to your network using something like Vagrant. And once Vagrant passes the automation check, it goes in and it pushes that into a branch for to propose changes. And maybe you have some type of automation server that pushes this config out to viral, which is CML today. And finally, you deploy those changes and unify your operation somehow over WebEx, right? So if you were in this automation space, likely you've done something very similar to this. And this is something that you had to implement as network automation engineer end to end, where you had to put all these pieces together. You had to configure all these pieces together and make sure that they talk to each other, and you got the CI going, and then finally the CD going, right? So who's familiar with this? Okay, now things are moving fast, right? We said, hey, network engineer, you're used to talking CLI. You gotta evolve and you gotta move into this whole space of automation. Use network APIs to automate. And we talked to you about this since, from 2015, 16, all the way to now. We gave you the tools, we gave you the skills to build on top of that. We're introducing AI, and AI is in everything. And so today, networks are changing and evolving to accommodate for AI. As network engineers ourselves, we also have to change. So we got to look at how AI is in our network and what is it that we need to know and understand in order for us to basically adopt and implement AI in our networks. And this is where that CI/CD pipeline changes on its head now. It's not really a pipeline, but it's more of multiple MCP servers that you have access to, the model has access to, and you are still sitting here with Carl on your side trying to figure out and implement those changes and those automated changes to your network. But the great piece about this now is you need to just understand how MCP works and what MCP is, and you let the model do the heavy lifting for you. While you operate that model, you operate that AI or that agent to do that and implement that CI/CD for you. Does that make sense? So you can see how it went from an entire pipeline to pretty flat. You still have an MCP server for Git that allows you to push and read and do all the GitOps operations here. You still have Ansible MCP server that allows you to make those changes to and apply Ansible playbooks. Maybe you have a CML MCP server that implements those changes before you push it out to your production network. And we have an MCP server for WebEx that allows you to basically have the agent push notifications out to your space. So the tools are still there. The way that we access the tools have changed. And this is why MCP has become very, very important in our journey, and something that as network engineers for our customers, we got to actually learn how to use it. And so with that, let's look at what MCP is. Who's familiar with MCP? Okay, so a few of you, it's going to be a review session. For those who don't know what MCP is, MCP stands for Model Context Protocol, and it's a protocol by Anthropic that was built to be an open standard to allowing you to connect different agents to the models. So models are expensive to train. Models don't know the context of our world. You get a GPT model, you get a Sonnet model. They don't know your network. They don't know your network configurations. They don't know the tools that are available that you normally use and leverage. So there must be a way for us to identify those tools and make the models know what those tools are, right? And this is where MCP comes into play. Think of it as a USB port for the LLM, where we can bring in our model, plug it in, and now we can bring in our data, plug it into our model, and now that model understands and knows the data that it has. MCP allows you to expose primitives, and these primitives come in a form of tools, which are actions, resources, which are data, and prompts, which are templates. And so when you're building an MCP server, you have these different tools and different primitives that you expose to the model itself, that the model is aware of the things that you want it to be aware. And it's super simple. It's a client-server relationship, and this is what, if we go deeper into MCP, we'll see what the architectural is for MCP. But I want you to this is something that a lot of us get confused when we're getting started with MCP. So MCP is not an AI agent. MCP allows you to build agents. MCP is not an AI assistant, and it's definitely not an LLM. MCP is simply a protocol, just like how we have a TCP, a UDP protocol. It allows you to basically connect data to models without you having to train the. And it's super simple to adopt, very simple to build tools against, and we'll see how simple that is. One thing that before we get into how this matters to us as network engineers, let's talk about the overall architectural of design of an MCP. So things that you should know. MCP is client server. You have a client, you interact with the client, it contacts the server, it sends the input to the server, the model knows what that server is, and it has access to tools via that server, and this is how you can access network APIs, WebEx, MCP. These tools are available via the server. So if we dig in a little bit deeper into this, MCP client lives inside the MCP host. You have a host, it's a client-server relationship, one-to-one. If you have multiple clients, they need a host so you can talk to the multiple servers. So an MCP client lives inside the MCP host. It speaks the MCP protocol, and it basically sends requests and receives response, and that's how you interact with the server itself. The heavy lifting, the thing that we need to know and understand is the MCP server. MCP server acts as the bridge between the AI agent, which is MCP Plus, and the real world tools and services. MCP server exposes the capabilities in a form of tools. So think of a Meraki network. Meraki network has APIs. Those APIs, you can access and pull data via those APIs from your network. If you expose that API as a tool in an MCP server, that model understands now that it has access to this API endpoint. So now it's hardwired into the model itself without it learning your network data. And what the MCP server does, it executes the requests coming from the clients and then ships back the output back to the client. And this is how we interact with all of this via the client. Does this make sense? Any questions on this? So you get the concept. I want you to learn a little bit. I want you to get a little bit deeper, and this is something just for knowledge that you don't need to. It's going to just help you to put it all together. So there are two different layers in the MCP protocol. You have a data layer and you have a transport layer. That data layer is built on JSON RPC 2.0 messaging protocol, and it essentially handles the lifecycle of MCP. It initiates, it checks for capabilities, it terminates connections, and also exposes those core primitives coming from the server. Now, there must be a way for us to send that data back and forth between the client and the server, and this is where the transport layer happens. And it's I want you to just, out of the transport layer, two things that you need to know. If you're hosting an MCP server locally, you're going to be using a standard IO as your transport layer. If you're looking at a hosted MCP or an MCP that's somewhere that anybody can connect to, it would use the essentially streamable HTTP for the connection that happens. And the data is then transported all over that data that we collect in the data layer is transported over that transport layer. Make sense? Okay. So this is the foundation of what MCP, and this is what MCP is. How do you get started with all of this? Well, there are a couple of things. You can go out and build your own MCP server for your use case. And there are standards out there that shows you how and what you should do to build an MCP server if it doesn't exist. A lot of the MCP is pretty new, so a lot of what we have from a Cisco product perspective, those MCP servers are being built today. There are MCP servers that are supported by the BUs, by the product teams themselves, but there are also folks like myself who need to demonstrate a use case where it's super simple to go out and build an MCP server. But because it's super easy to implement and build an MCP server and expose all these primitives to the model, to the AI, it's becoming a bit of a problem because everybody's building an MCP server. So it's the MCP Wild West right now. And one thing that I want you to be conscious of, because it's the MCP Wild West, security is not there yet. It's an afterthought. So be mindful, be conscious when you bring in somebody else's MCP server. Actually read and see what it does and what it has access to from your product or your network perspective. Okay, that's really important. So a couple of things. Look at, we talked about how it's client server. You need a client. You don't never have, you could go build out a Python client if you want, but you don't need to for MCP, because there are out of the box solutions like Cloud Desktop that allows you to basically integrate MCP with it. And I'll show you how that's working. But also what's great about Cloud Desktop or LM Studio, if you want to use a local LM as opposed to a hosted LM, what Cloud Desktop allows you to be, it allows you to connect multiple clients to multiple servers. So it acts essentially not only as your client, your chat interface, but also it acts as your host. So you can connect as many MCP servers as you want to that Cloud Desktop. So that's step one. We understood what the MCP architectural is. That's all you need to know from our perspective. You can go out and browse what is out there from an MCP server. I found this help to be very useful. There are plenty of MCP servers out there that you can leverage, or you can build your own. And there's a really cool Python library called FastMCP. This is what we typically build with, that allows you to basically spin up a server, an MCP server, pretty quickly. If you understand the product APIs, if you understand how the network APIs work, you can build yourself an MCP server. Okay, so why does this matter? And I'm going to answer this by giving you a use case that's going to resonate with most of us. We know that 45% of all network-related outages are based on configuration drift. You have a source of truth. You're running NetBox, for instance. NetBox is your source of truth. That follows your configuration for your network. Somebody makes changes to the configuration on your network. Your network takes a hit and it goes down because there's a configuration drift there. Also, as part of this use case, you have observability. We talk about this all the time with Splunk. It would be good to have some type of log source of truth within that use case. So you have NetBox running, you have your network running, and you have a log source of truth with all of this, where all the logs get pushed out to. Now, let's look at this use case. So let's say your customer is managing 10,000 devices, multi-site over a Meraki network. So I'm going to pick on Meraki. Really cool APIs, very nice MCP server out there that we can leverage. But Meraki, for instance, could be Catalyst Center. It could be, you could be using RESTconf. It doesn't matter, right? But for our key use cases, Meraki network, you're maintaining a single source of truth for your config. Excuse me. You're leveraging NetBox for it, and you've automated your configuration. You've done some really cool work with, going out when a config changes in NetBox, an event gets fired off to Meraki or a middleware somewhere. It applies those changes to Meraki. Meraki fires off events to Splunk, and it keeps track of all the changes and the logs and all of that. And this is perfect. And if we look at it in a perfect world, all config changes starts in NetBox. NetBox fires off a webhook. You have some middleware somewhere, a Python script, an Ansible script that's running that intercepts the webhooks from NetBox, and it makes changes, applies those changes out to Meraki. And then we also have Splunk running as a source of truth. Now, there's a little bit of operation configuration here that you need to apply and use to get all this use case and scenario going. But the hard part is when something happens, when a configuration drift takes place. And so enter Quinn. We all know Quinn. He doesn't follow the rules. So Quinn chooses to log to the Meraki dashboard directly. He changes the configuration. He ignores the configuration in NetBox. He saves, leaves, and you just lost the site because BGP is down. Now, what do we do? as network engineers, we have to go figure out what has changed. We have to go look at NetBox, have to go to Splunk, figure out the logs that who made the changes, what config has changed, and then go back to Meraki and fix those changes, and then make sure that NetBox is one-to-one with our configuration. It's time consuming. But now because we have MCP, we can simply have MCP do it. But what's great about the AI getting involved here is a couple of things. So with MCP, how we talked about it, in order to automate, before we get to the incident with Gwen, in order for us to automate, in order for us to manually look and build our use case where we are preventing configuration drift, we have to handle every single API call or build our Ansible playbook, or we have to make sure that we read the data from NetBox and traverse that JSON, extrapolate the data out, push it to our Meraki, which means you got to understand how the Meraki hierarchy works, and it becomes a little bit cumbersome, right? What's great about feeding all of these tools into MCP is you don't have to handle that logic. What MCP allows you to do is, hey, AI, I have these tools in Meraki. I also have these tools in NetBox. I also have these tools in Splunk. You figure out what to do with it. I'm going to question you, and I'm going to give you instructions, and you go do what you need to do. As long as I expose these tools out to the model, it's going to inference what it needs to do. Who's familiar here with the Meraki dashboard or Meraki APIs in general? So for those who are familiar with the Meraki APIs, you know, in order for you to access a network device, you have to traverse a list of organizations in your network. You got to pull that organization out from the organization ID. You got to go out and get the list of networks, and you got to pick the right network that has the devices that the configuration changed, pull that serial number, and figure out what happened with the configuration. You have to hard code that in your Python script or whatever automation you're using. If we expose 4 tools to the AI itself, which is get organization, get devices, get networks, get devices, and update config, the AI is going to know that the first step is to go, because it's been trained on the network, on the APIs, the Meraki APIs. It's going to know, then it's going to inference that I got to go here, ID, traverse this, look at the JSON payload, and go next. So we don't have to handle that. All we have to do is just build an MCP server. Now, this is for implementing our use case. Now, when the incident happened, we also don't have to do much work, because we can, now that it has access to all these tools, it could simply go out and say, okay, I'm going to check NetBox. I'm going to pull that data. I'm also going to check Meraki and figure out what changed. I'm going to compare the two, do a diff, print out a report for you, and then you can be the human in the middle to say, hey, okay, I want the config to be one-to-one again. You could go even further and go out to Splunk and find out when that took place, who made the changes, because we have a single source of log somewhere. So it becomes really easy for us to manage our network. We rely on the AI, and on the same account, we don't have to do any of the heavy lifting on our side to implement this use case. Now, if you want to get even more fancy with this, a true agentic operation, it could be fully autonomous, which means you see somebody made a change outside of NetBox, it goes back and fixes the change, and you have a self-healing network in place. Okay, does this make sense? So we can just simply let the AI do it. And the way that we're going to implement this, and I'll show you the use case, we'll demo it. I have about 10 minutes here. We have 3 different MCP servers, an MCP that talks Meraki, a server that talks NetBox, and a server that talks Splunk. We have a host, remember, client-server relationship. So we have a host that basically manages the 3 clients, and we have 3 servers running. And the model itself has access to all these tools that we've exposed. All right. So here's my client. I'm using Cloud Desktop. If I go here, you can see that I have 3 MCP servers. This is my Meraki MCP server. it has tools. These are the tools that the model has access to. It has get Meraki org, get network by org, and you can see the list of tools that are exposed as part of the MCP server and so forth for NetBox and Splunk, right? So I can simply say, okay, and I made some changes to my configuration, my Meraki sandbox before this session, but I can simply go and say, let's do this. I want you to act as my senior network engineer, check my Meraki config for Cisco, specifically for the Cisco U organization. I'm managing a bunch of orgs. I only care about one, and compare it to what's in my NetBox, and give me, which is my single source of truth, and output it for me. So look, I notice how I didn't have to define where to go from an MCP either. It knows that first it needs to go to Meraki, so it's going to leverage the MCP server. So I'll help you get audit. So it went to get organization. I didn't tell it any of this. It found my Cisco U organization. It pulled networks and knew net and inference and knew from the model being trained on our API docs that next is get network and next get device by network. Now let me query NetBox because it has access to NetBox itself. And it gave me a report. And identified some critical things. My Meraki config is off. It looks like these devices that are in my Meraki network and my NetBox, this Meraki configuration is off. It in my source of truth is at 192.168. However, it's at 10.10.10.100. So somebody made a change. And it's giving me all this information, and now it's telling me also that the switch name is configured differently. In my NetBox, it's called Campus Switch, and in my Meraki, it's called Cisco Meraki Switch. Now, we can't have that because now there's a configuration drift, right? So I want to find out who made these changes. Can you check Splunk? Hopefully there's a Splunk event. So it went in and it checked the health of my Splunk server. Good, Splunk is connected, and it's gonna go pull in the list of indices in my Splunk dashboard or my Splunk instance. Again, I didn't have to tell it which indices. I have about 10 different indices in my Splunk. It's gonna go and pick the Meraki index itself. Because we're talking Meraki, I saved my stuff in Meraki index in new, and it starts querying Splunk. Who here has used Splunk? You can, it's the query language itself has kind of very finicky, right? And so putting that on the onus on the AI to manage and pull and do the search queries for us is really, really great. It simplifies things for us. And you can see it got errors, and it's gonna keep trying. Perfect. So it kept trying until it actually got a hit. And here's the data coming back from Splunk. That's the JSON payload. And it'll tell me, okay, excellent. Now that I have a complete picture, here's the forensic audit report that it got. So all the changes were made by user Kareem Iskander. Here are the changes that happened. So the old values were these, the new values were this. And it's pulling this information from my Splunk instance. And it gave you a log of all the changes when it happened. And this Kareem dude has made a lot of changes 4 times. And then even pulled the root cause analysis for you. So, okay, but cool, we know all of this, that we can't have a configuration drift. Let's just tell the AI, okay, it's time to match what's in NetBox and fix the issue. Go do it. it's going to read data. It's going to, because it has now access to update configuration in Meraki. It's going to, again, pull the list of devices, pinpoint exactly which devices it knows it has changed from Splunk, and it's going to revert back my configuration. And it's matched it. It renamed my devices. It updated the IP addressing on my devices. It's fixing the campus switch IP address, and it's built that payload on its own, and our network is back matching to what's in NetDevOps. So you can see how impressive and how cool this is, and I can tell you, you'll see if my resource section, all the MCP servers that I built here are maybe 15 line of code in Python using fast MCP. So it's super simple to get started. It's really powerful. This is how AI plays in our world, and it's. I think it's time for us to leverage all of this. Okay. Any questions? Yeah, that's a good question. Let's chat after. There's a tool for you. All right, some resources for you. Everything I talked to you about, if you're looking to get started with MCP in general, there are Cisco U tutorials out there for you. So check those out. We just released 2 brand new MCP tutorials last week. Do those if you're looking to get started and get hands-on. Email me. I'm on WebEx. Go to my LinkedIn. I have a blog series around AI for network engineers. Here, there's a new one that's coming out next week. My 2 previous ones is about around this session, and I give you hands-on and links to my GitHub repo. So if you want to download the code and get all of that information that we did, just go to my GitHub. It's there for you. Hopefully this was informative. I hope you had a good time, and thank you for attending my session today. Appreciate it.
All right, we'll get started in about 90 seconds or so. No rush.
Sure. What about it? You want to store it somewhere?
Yeah, what is the best price?
Not locally. Whether you want to put it into, especially if you're doing shared services. So when you're doing a shared service Terraform model, whether you're using like Terraform Cloud as your backend or whether you're storing it like S3 or some other remote store, you definitely want that in a location where it is redundant, backed up, and accessible for everyone who's going to be operating on that. So if you're using Terraform Cloud naturally, it's going to store the state in their own remote backends. If you're using Terraform on-prem, best practice is to sub it either in some remote share or in like S3 or something like that. Just depends on where your guardrails are set. But definitely don't do what I do and store everything locally on my laptop. So, but I won't talk about Terraform State because that's like the super advanced ultra stuff. Hopefully I'll get that session picked up. Probably not in EMEA this year, but possibly in the States, and I'll bring it back around. Not quite ready for that yet, apparently in the Terraform practitioners. But that being said, it is 2:00. I will kick this off. My name is Quinn Snyder. I am a technical advocate with Learn with Cisco. So everything we see here. Prior to this, I was a developer advocate with Cisco DevNet, and so I learned just a lot about Terraform. And it's kind of like my favorite programming language. You always have that. You have your first love, right? And then you have the one that you enjoy hanging out with a lot. And this is I do a lot of Terraform here. So I kind of divided the session. Well, first of all,
I believe that all of the slides will be in the Cisco Events app. Whether if they're there now or whether they'll be there at the end of the conference, yet to be determined, because I was a little late in uploading them, so my apologies. However, I will give you a QR code to all of the presentation and code at the very end of the session, so it's like incentive to stick around so you don't leave too early. But you can also join the discussion with the WebEx space, or you can find me online in a variety of social media, as well as you can WebEx me directly, email me. Just find me on the floor. I'll be here all week. And we can talk all things Terraform. So I've divided this session. It's going to be a little bit of a quick hit. This was a Cisco Live session that we've condensed to fit here in the theater for 30 minutes. I've kind of divided the content into two different sections. The first part, so we'll talk about TFN, the formatting and graph. So those are kind of like creature comforts, nice to have things when working with Terraform. Not necessarily critical to what you're doing, but they're nice ways. They either demonstrate nicely or they show what you're doing, or it makes your life a little bit easier when managing Terraform. So we'll do that at the first part. And then the back half, we'll actually get into the meat and potatoes of like hardcore or more hardcore Terraform. So we'll talk about Terraform console and modularizing Terraform configuration. And then we'll wrap it all up, like I said, with that QR code for all the sample stuff as well. Before I get kicked off, how many folks are using Terraform today? In production? Brad, you don't count. Okay, no, that's good. So I like I said, I divided this up into two different sections. Hopefully, I cover enough different stuff that everyone gets to take away something from it. So even if you're using it in production, hopefully there's something you can take away and use in your own environment. So we'll start with the easy stuff, managing Terraform versions. So we've all downloaded Terraform. If you have not, I guess there's a couple different ways you can go about it. Easiest way is downloads at terraform.io. You can download the individual version, and then it creates a single binary. Now, I've talked about this in other presentations where Terraform is written in Go. So for those who are not familiar with Go as a programming language, it's very close to like C and C++. It's a strongly typed compiled language, which means that it's great in the fact that everything gets put into one executable file, and you can move that file into your executable path wherever you need to, but you're kind of on your own for things like semantic versioning and things like that. Every binary is self-contained. And if you download that file from Terraform, whether I choose, what I have, 196 or 185 in that screenshot, that's a little bit old, whether I choose either one of those versions, it's just going to give me a file called Terraform. So as I increment my versions, I need a way to handle that semantic versioning, because as new features are released into Terraform, the providers will follow along. So if I'm using those current version of maybe AWS's provider, there may be features in there that may not be backtracked to an older version of Terraform. So I have to manage those things automatically or on my own. Now, ordinarily, if I'm just doing dev stuff, that's not a big deal. I just upgrade to the latest version and we're off the races. But when I start putting that into a CI/CD pipeline, or I'm using things like TerraGrunt or Atlantis to build these things, that becomes very critical, especially if I'm in a multi-tenant, multi-user environment. So if you're doing regression testing or experimentation on your own systems, it's nice to say, I'm at my current version. I want to move up one or two versions and test before we implement that in the pipeline in production. So it's easy to download, easy to install, but you're still on your own for semantic versioning. Now, there's a couple of different tools that are out there. The one that I've used the most recently has been TFN. So if you're familiar with Python or Ruby development, there's tools called PyEnv or RBEnv. It's a shim that gets installed onto your system that allows you to manage Terraform versions automatically. So I can either install, I can call a certain version of Terraform for installation, or what I use most often is I have a file reference within a directory called .terraform version. As soon as I move into that directory, it will automatically switch the version of Terraform that I'm in that working directory to the appropriate version. So if I have a dev environment that's maybe using 1.12 now, but my prod environment is using 1.95, I have two projects, dev and prod, on my laptop. As I move back and forth, it will automatically move Terraform versions for me. So it's a nice thing to have. So you don't worry about the semantic versioning on your own. It's all handled by the utility that is installed. The other important thing is this supports all versions of Terraform. So if you saw previously in that screenshot, I have the major versions 1.9, 1.8, 1.7, 1.6, etc. I can only download the latest version, the latest minor revision for that major version on on Terraform.io. If I'm, say, running 193 in production, I can't download that directly from Terraform. I can install that using TFM. So it gives you access directly to those versions as well. They're just buried on Hashi's servers, but it makes it easy to do that. Second piece of it is, for those nice to have, is making your Terraform files easier to read. Now, I mentioned earlier that Terraform was written in Go. The nice thing about Go is it's strongly typed, and we don't have to worry about things like white space indentation like we do with Python as much, right? So when we build things in Go, we have well-defined structures and types as well as syntax. So when I write my Terraform plans need to follow a syntax, but it's delineated based on curly braces. Like we've all seen what Terraform looks like, our HCL code. So all that matters is, are things put in the right way in terms of character returns and curly braces? So it can be very hard to read, especially if I'm building large maps of variables or I'm doing a lot of local variable manipulation. It can be very hard to read if I'm not following proper hygiene, I would say, as I'm building that. However, there's a utility called Terraform FMT. And what this does, so over here on the right, sorry, it'll be your left-hand side, I had to think about that for a second, is a sample Terraform inventory variable that I've built. This is for some kind of fabric deployment that I was doing. You can see, for those who have not used Terraform before, I have these individual pieces that are delineated by the curly braces here. So I've got curly braces that kind of ensconce or delineate between individual variables. So I've got spine 1, spine 2, leaf 1, 2, and 3. Each of those is a map, and that map is bounded by the curly braces. And then I have different arguments inside there. So I've got names, IP addresses, and roles. Now I have everything aligned on the left-hand side, which is completely valid. I can run that as an inventory variable. I can run that as a Terraform plan, and it will work just fine. However, it can be a little bit hard to read and pick all that information out. Kind of a creature comfort or something that's nice to have. But if I'm debugging large Terraform plans of several hundred lines, I don't want to be reading everything that's left justified. So when I run Terraform FMT, not only will it break these things out into the nest that they are based on the curly braces, what I will show in my demo is it will actually align things based on the equal sign. So if I have longer argument names, so key value pairs, if my key or value is longer, it will automatically align my equal sign to make it easy to read and pick those things out. So again, not necessary, something that's very nice to have as you do that. And it's part of, if you're building, whether it's Terraform providers or you're writing Terraform code in general, FMT should be part of your linting process before you push to prod anyway, to make it easy to read. Now, the final thing I'll talk about is the visualizing the graphs, and then I'll do a demo of all these three things together to save on time. So how many people are familiar with the back end of how Terraform works with the redundancy graph and mapping of all that? It's pretty cool, right? So what I talk about normally, especially when people ask me as a comparison between Ansible and Terraform, is Terraform is end state declarative. I write what I want my end state to be, and Terraform will figure out the process to get there for me. It does that by building a resource graph for that entire Terraform plan. So I say, I'll use ACI because that's what I'm familiar with. But in ACI, if I build a tenant, and then I want to build a VRF, and then a bridge domain and subnet, and maybe I've got contracts or EPGs inside of there. If I was building that in Ansible, I would need to build it in a very specific order, because I cannot assign a VRF to a tenant if a tenant doesn't exist ahead of time. In Terraform, I can write that in any order. So I can define my subnets and my bridge domains before I define my VRFs and my tenants. And it figures that out by building that resource graph. Now, if you really want, if you cannot sleep at night or you have a really long flight, that QR code will take you to Hashi's resources on resource graphs. It's interesting, but it does make for some good sleep if you read it. So this resource graph is generated at all stages as well. So it's not just done at apply, it's done during my plan state as well. Because we know if we do a Terraform plan, it also has to consider our previous state that we've built and create that resource graph accordingly. So it does it at all stages, not just our apply, and it uses all files in our project folder just like we would if we were executing Terraform within a project directory, right? Because we have variables.tf, outputs.tf, provider.tf, main.tf. All of those things need to be considered as part of that resource graph. So you may say, Quinn, why do we care about this? Why is this a nice to have? Because once we do a Terraform init, we can actually visualize the actual order in which things will be applied using this Terraform graph command. So by default, it will build something in what's called a dot format, which is a graphical representation. I'll show you an example of that in the next slide. So it will build what the output of this Terraform run will do. So if I'm doing a Terraform apply, it will show and allow you to visualize what's actually going to apply when we perform that Terraform apply command. So by default, it's in a dot format, but it can be converted to a graphical format using GraphViz. So for those who are unfamiliar with the dot syntax, this is something of building an ACI tenant with a bridge domain and VRF and some subnets. You can see that it's kind of got this root declaration. We've got labels, we've got shapes, we've got these outer notes. But we can convert this to an actual graphical representation using GraphViz, and I'll show that in a second. So before I jump into the real quick demo of those three things, any questions so far? We learning something a little bit new? Okay, just making sure. Okay, so let's do this. So we have, I'll start with the Terraform FMT. Like I said, we have this just a source file, just a text file of all of the different items that are in here. So I have this, I've got some maps, I've got some different variables here around leaves, I've got usernames and passwords and all these things that are visible, just a standard Terraform file that I would ordinarily work on and write. But you see everything is left justified there. So what I'm going to do is move into the O1 format. You can see I'm right there. I'm going to copy the main to main.tf. So we can see that we have this new file called main.tf there. And just so you see that there's nothing up my sleeve, I have it there. It sees it as a Terraform file, and that's why we get the syntax highlighting, but I haven't changed anything yet there. So if I go back into the directory and I do Terraform FMT, oh, I've got something wrong here. So line 4. Oh, that's why. There we go. Try this again. Okay, so we run that command. We get no output, but if I go back, you can see that's now changed everything, so it's indented and aligned appropriately. So we saw what move was before to what it was after. And also, as I get into these large inventory files, you see that they're nested, but everything is appropriately aligned based on that equal sign. And that will change based on where I'm at. So you can see that my leafs are all aligned. So if I'm using something like cursor column inside of VI or whatever tool, I can see where I'm at in terms of the nesting just based on those alignments there. So that's the Terraform FMT. So let's move into the graph. Actually, let me go back one more. So what I said before was, I'm going to kill two birds with one stone here. So Terraform version. You can see I'm running 198. So I'm running an older version of Terraform inside of this O1 FMT folder. So nothing up my sleeve. Let me clear that so you can see it a little bit better. 198. I'm going to move into the second folder called Graph. You can ignore the Mies error there. But if I do a Terraform version here, you can see that I've switched to 110.5. So that's that TFN that I was talking about before, because inside of here I have this Terraform version file, which it's just one file that says 110.5. So by moving into that directory, TFN says, I see that version, and I'm going to switch to it. Now, what I did not show, because I didn't want to trust the Wi-Fi, is if I call a version in this file that I don't have installed locally, as soon as it will still show that I'm using an old version, but if I try to do a Terraform init or Terraform plan, it will then download the appropriate version and then perform that function. So I can do the manipulation right through there. Now, the other thing that I have in here is this main.tf. So let's look at this. And this is just a standard Terraform file to, again, provide that bridge domain and context and tenant. So I have my source provider. I have some variables that are in there. I have my bridge domain, subnet, context, and tenant. So I have all of that defined. So what I'm going to do is I'm going to do a Terraform graph. And I'll do this first part here. So this is the output of that Terraform graph. If I just do, if I just want to say, do a Terraform graph. So in this case, perform a plan. So I'm not doing apply action. So just what was going to happen if I run the plan action, and then draw cycles. For those of us who have had to do Terraform where you've had to do a depends on, or you've maybe had to do a parallelism command to slow down the Terraform application, by doing the draw cycles, it makes sure that I catch those separate parallel tracks as it has to go through and iterate over multiple variables there. So the Terraform graph will give me this output here. But you say, what if I want to visualize this? So let's do Terraform graph pipe. So all I'm doing here is I'm typing this to graph is output files a PNG and give me this tfcycle.ping. So in that, I should be able to just go here. Oh, it's not going to show up. Give me 1 second. You'll get this image. So you can see that I have this whole file. So I have the root of the file. It's going to grab that provider from the registry. I have my subnet, bridge domain, VRF, and tenant all tied. And you can see where the variables peel off of all that. So it allows me to visualize how that is being built. Yes. Okay, so the question was, can you limit the scope of everything? By default, it's going to read everything that is there within your Terraform plan. So the idea is, if I'm building Terraform, I don't want to limit the scope of my Terraform application unless I move into that. So by default, no, it's not going to be able to limit the scope. Now, if you have like sub-projects or things that are in there, modules, you can call those individual modules as part of the graph. But Terraform, again, because Terraform is that end state declarative, I can't. It's just like OSPF. I can't have half of my LSDB and still have a full picture. It's the same with Terraform. I need to have the whole picture of what I'm applying. Yeah, you can peel it off after you pipe it, but by default, Terraform graph is going to grab everything in that file. Okay, so those were the real quick creature comforts. And now the fun part. Interactive-ish Terraform. So how many people know of Terraform console? Okay, good. This is the fun part here. So when we start off writing our HCL for Terraform, I tend to follow this circle of pain. I write HCL, I do a Terraform plan, I apply it, something is inevitably broken, and then I have to go back and fix it, right? Now, if I'm doing basic Terraform, I can usually just do 3. But if I'm doing complex variable manipulation, or I'm piping stuff to locals, or maybe I have some kind of data model that I've got to then break out and apply in different ways, I always mess this up. And it takes 5, 6, 7 times. And if I'm doing something in AWS, then I have to destroy and then reapply. Like, it's a whole mess, right? So how do we interact with Terraform HCL configuration ahead of time so we can kind of limit the scope of this? And maybe this is a happy circle, not a sad circle. And that's where we enter Terraform console. Now, I will say this. The Terraform console allows us to interact or interrogate our Terraform or HCL plan. We can look at variables, we can look at configurations, we can look at state. The Terraform console is not a REPL. So if any of you have invoked Python from the command line, Python-I, Terraform console is not that. Because again, going back to how Terraform works, if I invoke Terraform console, it's going to pre-build all of those things that I'm going to apply with Terraform. It's not going to do a full apply, but it's going to build that entire resource graph. I can't change that resource graph midstream because that's compiling, bear with me, that's compiling my Terraform. So I can only interact with what I have declared as part of my Terraform files. So if I want to say, I'm going to add a new variable and test this thing out, I cannot do that. It's not interactive, but I can see what it has already built when it's done the compilation. So there is no Terraform REPL, but we can do some really cool stuff with Terraform console. Let me jump over to that demo. Okay. Oops. All right, so we'll open this simple interrogation here. So we see that we have some information here. We have this locals. Let me close this here. Let me close this here. So you can see we have this variable called locals, or this map called locals. We have a bunch of variables stored in here. For those who are not familiar with Terraform, locals is like a holding pattern for variables. So I can build a data model. I can ingest some data there. I stick it in locals and I do some manipulation with it without having a full-blown Terraform file if I want to. So while this is not a full Terraform HCL file, I can still manipulate those variables just by having them inside of this locals file. So you can see I have an empty variable called leafs. I have a session ID in there. I've got a map for user information. I've got some information on fabrics, things like that. So I've got a bunch of different kinds of variables here. So let's start by just doing some real basic stuff. So let's yank this. And let's go Terraform console. So if I invoke Terraform console, it just drops me. And what I'm going to do is I run this first command called split. So if we look at that variable called, let's see here, boop, boop. So we had that variable called leaf4. So that was a map that had a description, a username, password, IP, and role. So what I did is I split that. So I said split based on the period, the variable local leaf4 IP. So find local leaf4 IP. So go through that nest and split it based on the dot delineation, which gives me a list there. So real basic stuff. I can also oh, there we go. I had an extra character return there. Okay, so if you see at the bottom, let me clear this out real quick. I don't like the layout here, but there. So, like I said, it was a list item there. So that original one was a list. So now we're just going to say split that local leaf4 IP, but give me the third item in that list, or it's 2 in the square brackets. So it gives me the 20. So it was 10, 10, 20, 175, or 176. So give me the third item in that list, and we can call that out there. So really simple kind of interrogation. And let's go back to 04. So in this one, we have this main.tf, which is a list of maps. So this is where I talk about that really complex data manipulation. So I have this map that has two key value pairs, another map that has 2 key value pairs. And what I want to do is I want to iterate so that I have item 1A, item 1B, item 2B, and item 2C. So that's a pretty common use case where we have some kind of tenant. We want to have multiple VRFs for that inside of ACI or some other thing. We want to flatten. We want to perform this manipulation. Now, I won't get into the machinations behind this. I just have this variable called squash where I flatten those items, and then I do an iteration over the list of maps, and then I pull those values out and recreate a new structure based on the return values from each of these 2 maps. So, as part of that, we can validate that by sorry, let me move that up. So this local.squashed, so it's already performed that manipulation, right? So when I invoke Terraform console, it's performed the action that was called in that variable. So it stored that variable as local.squashed. And now I've pulled those things out. So I see item 1. So I've got A item 1, B item 1, B item 2, and C item 2. So I'm able to validate that manipulation ahead of time before I stick it in my Terraform file. So I know what I'm doing ahead of time. So I'm not trying to debug the whole thing. I can debug my variable manipulation and go from there. And I'm going to do a couple of more things here because I really want to get into 05. Manipulation piece of it. So in this one, oops, Control B2. Okay, clear this. and cat main.tf. So in this variable, I just have the same kind of thing I had before. I've got my local values for leaf, session ID, inventory files, etc. And I have these demo VRFs. So the last thing I want to talk about before I jump into the modules is, and you can see these commands here. There are some things, because Terraform is strongly typed, I have to be very careful with how I define each of my my variables. So just like in Python, square brackets denote a list. Curly braces denote a map, or what's a dictionary in Python. And if I call these things, I have to make sure that I define them the right way. So in this case, if I wanted to, so for every item in the Fabric inventory, give me the name. So I pulled out the names of that list of maps there. However, if I call that the wrong way and call it with the curly braces, because I'm doing a list, it will say invalid expression. So we have to be cognizant of those items. We can call things using the star operator. So instead of having to call the specific name, just give me everything. So as before, we had the inventory 1, 2, 3, 4, etc. I can use that star item to give me all the items in there. And I can also do some remapping. So this is the last thing I want to do. So for key and value in the local Fabric inventory, just give me the key value. I'm not doing anything specific there, but I'm saying for the key value, I'm creating new maps essentially within Terraform. So nothing fancy, I just created a new map there. But I've pulled the items out, I've created a list, I've staggered them out. So you can do a lot of manipulation using that arrow operator inside of Terraform. I know that was quick. Please play with the sample code, because there's a lot more things that I walk through in the repository. I do want to talk about Terraform modules. How many folks have played with Ansible and Ansible roles? Okay. Terraform has an equivalent called a Terraform module. What that allows us to do is abstract a bunch of complexity away from the user and define the output that I want to build without having to define all of the individual Terraform code. In this case, in my example, I'm creating a whole ACI construct, but I'm only exposing two variables to the user. Give me a subnet IP and give me a name. From that, I can feed that input. It's going to build everything there. I don't have to worry about all the individual pieces behind it. They just worry about providing me those two names. So Terraform modules allow us to simplify automation by defining things that we want to do repeatedly, and create kind of the abstraction for that configuration. They can be from a project folder. They can be called and stored inside the Terraform registry. So if you go to registry.terraform.io, you'll see there's providers and there's modules. So there's published modules on the Terraform registry, or if you're just pulling them from a remote Git repository within your environment, you can pull them from there. You reference them in main.tf and abstracts the underlying work. And I'll show what I mean there in a second. But we only want to do this if we're going to simplify the configuration, prevent configuration issues, or we want to reuse configuration, are the three key points there. So let's go back here. All right, so I have this module set up. Now in here, this is my main.tf. So in my folder structure, I have this modules and I have main outputs and variables in here. So you can see in this main.tf, I've just called my ACI provider. I'm calling the module called ACI tenant scaffold, which is what I've called that module. And I've called the source, so I'm using it locally. I'm not calling it from the registry. I'm not calling it from Git. I build a tenant, and it's called aardvark1. I've only called it that because the 2As are going to show up first in the DevNet sandbox, and give it a description, and then I call a subnet block. So I'm going to build a whole ACI tenant just by giving it a name and a subnet. Now that's possible because in the modules folder, in this ACI tenant skeleton folder, I've defined a main.tf outputs and variables. So we'll look at this main.tf here for a second. And you can see this is where the meat and potatoes of that configuration are. Now, even if you're not ACI familiar, we can see that we have the provider configuration that says where we're going to log in as a variable. We're going to build a tenant, we're going to build a VRF, and we're going to build a bridge domain and a subnet. Now you can see what I've done here, and this is another piece of Terraform manipulation. $ allows us to do variable interpolation. So I'm going to call the name of that and put it in there, not just reference the variable, just give me the name and stick it in there. So I've pulled out based on some variables there. And then finally, I have the subnet, which calls that subnet that I referenced earlier at the very top of it. And then finally, just for being fully transparent, there's my login information to the sandbox. And then I've just provided some dummy variables, tenant, VRF, bridge domain, and subnet. There's no default configuration there. I've just defined the variable type. So in theory, if I go to here, and I do a Terraform apply. Oh. You have to do a Terraform init, so it's going to find the module, and then it's going to find the provider. We're all set to go there. So now, assuming that the Wi-Fi works, it's going to reach out to the DevNet sandbox and actually build that tenant. And at the output of this, we'll see that we've created the bridge domain name and VRF name to make sure to show you that it's pulling those variables out and applying them as part of the configuration. In theory, that tenant should show up here. This is running really slow, though. So what I'll do in the meantime here, just to show you that Terraform graph command one more time. And then go back here. So this is that full Terraform resource graph that we built as part of that module. So you can see all of the output from all of that. And this is a little bit confusing or hard to read here. But you can see that it's called the module as well as the individual provider and pulled the variables in around in a loop there. Yes, sir. By default, that's a good question. I don't know. By default, it's not going to because they're insecure. So it's not going to give you the actual name of them. It's just saying we're pulling it from this value and you've got to go build that. I don't know if there's a way that you can actually pass those into the graph command because it's not going to pull that information. It's just showing the order in which they're built. Let's see if that actually showed up. Nope. Okay, we'll just go back to the presentation. All right, I know that was quick, and I know we're a little bit over. This is the QR code that I'm sure everyone's been waiting for. GitHub.com/QSnyder DevNet 2565. It's a different session, but all the stuff is there. QR code will take you there. Gives you the command list, the sample TF files, and then that configuration module that I built that's very rudimentary, but you can start playing around with it on your own if you choose to. And I will leave that up. But with that, thank you so much for giving me 30 minutes of your time. I know it's fast. I know I talk fast, but thank you. And I'll be around all week if you have any other questions.
Oh, is it better? It works? Okay, thanks. So we'll start in just a few seconds here. All right, welcome everybody. Just do a quick sound check if you can hear okay. Just give me a thumbs up if the sound is okay. Thumbs up around? All right, excellent. So my name is Rob Barton. I'm a distinguished AI engineer. Welcome to our session today. So I'm going to talk about this field of AgenticOps, what it is, what we're doing, and how we're developing certain products. And I will focus on one called AI Canvas. It's very, very exciting technology that we're developing, and it was announced at Cisco Live, the previous one in San Diego back in June. I'm also going to talk about our strategy towards LLM and model training and how we're developing internal models. And the back half, I'm going to talk about exactly how we go through this process of fine tuning and are able to take a fairly small model, but make it very, very good at solving networking problems. So what is AgenticOps? So AgenticOps, of course, we've moved in this world from just talking about LLMs to agentic AI. So this is what you can do with agents. So I often think of agentic AI as, it's like a human brain. It's like an LLM. It's very good at responding. It can answer questions, but a brain on its own can't do much. You need arms and legs, and you need things to actually go and make things happen. That's what agentic AI is like. Agents are software functions that the LLM talks to. So it's like the arms and the legs that let the LLM have actions to do all kinds of incredible things. So when we talk about agentic AI, this is now, of course, where the world is focusing a lot of its attention, where a lot of development is happening. For Cisco, this is very important because operationally, how we operate networks, how we operate security, it is fundamentally changing the direction of how we will do things in the future. So what we're developing is not just a product, it's actually a seismic shift in how our customers, partners, and everyone will be interacting with the network moving forward. This could be automating the network, troubleshooting problems. This could be looking for compliance of a network to certain things, talking to your network and asking, how should I upgrade you? This is the world of what AgenticOps will do. So as we go through and build an AgenticOps system, AI Canvas, these are the 3 design principles that we are using. First of all, it has to be a cross-domain type of a platform. And that's natural because Cisco builds technologies across security and cloud and Wi-Fi and campus and branch. It has to be cross-domain. Let me give you an example. So how many of you in your companies use WebEx today as your primary collaboration platform? Okay, a couple, yeah. Who uses Microsoft Teams? Okay, a lot more. So I'll use Teams. So let's say one day someone calls up and say, hey, Microsoft Teams is acting a little slow today. Doesn't act very well. Okay, so we got to go solve a Microsoft Teams problem. But wait a minute, is it really Microsoft Teams? Or is it Azure Cloud? Or is it the internet that's having problems? Do you remember AWS had this big outage 2 weeks ago? It was a DNS outage. Okay, it could be a DNS outage. It could be your SD-WAN that's got a problem. You see, those are crossing domains. If I want to solve this problem, why is MS Teams slow? I cannot solve it just by looking at the network or just at Teams. I have to look at everything. So an agentic ops system has to be able to be cross-domain. The second thing is it has to be multiplayer. This sounds like a video game, but it's, of course, it's similar, multiplayer video game. If I'm going to have people from multiple domains helping me, that makes the system multiplayer. Now, you go talk to ChatGPT or Claude or something, that's just you talking to ChatGPT. But what if you could bring in your colleagues that are helping you solve a problem as a collaboration space? Now it becomes multiplayer. We're working together instead of just passing this down from team to team. This accelerates my ability to solve a problem very, very fast. The third design principle is that we have to use purpose-built models. Why is Cisco building its own LLM? We call this the deep network model. There's other models out there which are fantastic. GPT models are amazing. You got Claude models. You've got Mistral. They're amazing models. And when we tested them, they're very good at answering questions even about networking. Where they struggle is the reasoning through troubleshooting steps. Take the knowledge and the experience of a CCIE with a decade of experience. How do you train that into a model? Right? Models have been trained on documents which give you, the basics of how protocols work and how you configure things. They don't take a decade of experience and put that into the model. That was the gap that we realized needed to be filled. So the deep network model is trying to fill that. It's the difference between just knowledge and experience to make it a reasoning model. So we train it with things like Cisco TAC. TAC, we can see 1 million cases a year. Once we start to train it on the methodology of how cases are solved, we took a look at Cisco University, Cisco Learning Academy. This is where the deep network model becomes very, very powerful. In fact, now you compare the benchmarking. Benchmarking of deep network model, it still benchmarks even better than GPT-5. How many parameters are in GPT-5? Well, nobody knows because they never published it, but it's estimated between 5 trillion and up parameters. Okay. A network model is based on a foundation of Google DeepMind's Gemma model, which is 27 billion parameters. So we have a 27 billion parameter model that out benchmarks a 5 trillion parameter model. That's what happens when you fine tune a model, how to reason through networking problems. And what are we able to do? Well, we're able to solve problems like wireless experience. Why is like Wi-Fi slow? Where are my holes? App performance issues like why is Microsoft Teams not performing well? Take me through the steps how I would solve that. How can I onboard clients and figure out why clients are not coming on quickly or why are they taking a long time to authenticate? These are the typical problems we face in networking as network engineers. That's what we train into our model to be able to solve very quickly across multiple domains. The deep network model is the heart and soul of AI Canvas. So AI Canvas is our AgenticOps platform. It is meant to be cross-domain. It is meant to solve networking problems across the internet, around Meraki, around Thousand Eyes, data center, security. In time, it will be fully supporting the entire portfolio of Cisco. So from a natural language, so you have an AI assistant. Here you can see this is where you put your prompt in. You will talk in natural language. You know, why is Bob's Microsoft Teams slow? You will just ask it there, and it will know the context. It'll reason through, and you won't have to tell it how to solve it. It'll start to pull data from Thousand Eyes. It'll pull it from a DNS server. It'll pull it from Splunk, and it will be able to reason through step by step as a human would, as a CCI would. This is like your CCI who doesn't sleep. That's the intent of what we're building. So our business unit, we are now in the alpha of this platform. It's going to be going into control general availability within about 6 weeks. And we are hoping by early into 2026, we'll have it available globally. So this will be available on the Meraki dashboard day one, but it will be in other platforms down the road. So that's our intent. We want it to be truly cross-domain. So if I have a problem, you know, with some packet loss, well, is it the firewall that's dropping the packet? That's else in the switch that's flapping. It needs to be cross-domain across everything that Cisco builds. And that we work with our customers. So the idea of AI Canvas, it is going to be this AgenticOps system. It will be really driving almost like a co-pilot for your entire system across our portfolio. Okay, so we're going to build this kind of system. If we walk through, I want to take you through the steps of what an agentic system actually looks like. So you get this intuitive sense of agents and models and how they all interact. So let's say we've got this user. Imagine you're sitting in front of AI Canvas one day, and Bob's Microsoft Teams is slow. So you go, hey, AI Canvas, please help me figure out why Bob's Microsoft Teams is slow. So you're talking to an agent, right? This agent is just a software program, but it has to talk to the model. So it's going to talk to the LLM, which is our deep network model, and it says, oh, this seems to be a problem about performance. This is a problem about an application. Now, how is the LLM going to solve that problem? This is what agentic AI is all about. It's the LLM has to interpret the prompt and figure out what to do next. Now, it doesn't know the answer yet, but what it's going to do is put a plan together. So the first step is create a hypothesis to make a plan how I would solve this problem. Now, it's like like a detective solving a crime. Before they can go and solve the crime, what do they have to do? Well, they have to go interview witnesses, visit the crime scene, collect evidence. Right? This is the basic steps before you can solve a crime. Well, our crime here is the Microsoft Teams is slow. And the LLM is going to have to figure out what are the steps involved to go and solve that. So he says, okay, well, I think we need to go and talk to a few backend systems. And he says, if we go talk to WebEx, okay, Microsoft Azure, we talk to Thousand Eyes, we talk to Splunk, there's where the evidence sits, right? If we talk to these backend systems, they can help us solve this problem because they've got this insight. So the agent says, okay, that sounds good. I'm your arms and legs. I'm going to talk to these backend systems. I'm going to get the information you need. I'll send it back to the deep network model. And here's what you asked for, and now we can go and solve the problem. And he now is able to reason through it. He's got the problem statement. He knows the domain. He knows, he's looking at the evidence. He starts to sort through. He reasons through it, and he says, okay, I have the answer for you. It's like maybe you don't have quality of service configured correctly, some of the problem, perhaps DNS problem, but he'll give you the answer. What you're looking at is a very typical architecture of an agentic AI system. The top is your model layer. So you have multiple models. It doesn't have to be only one. You can have multiple. You have agents, which are simply software functions which execute code on behalf of the model and at the instruction of the model. So they only execute what the model tells them to do. The bottom layer are what we call tools. Tools are the software that holds the data. This is where the answers lie. So this is a very typical agentic architecture. It's abstracted. This is what AI Canvas basically looks like behind the scenes. Now, how do you build this at scale and how do you make it work? Let's see a show of hands here. How many of you are familiar with a new protocol called MCP, Model Context Protocol? Okay, I'd say 25%. So a little context. So MCP is a new protocol that helps us build and scale this. 1 year ago, Anthropic, the company that built Claude, they realized, we're going to build all this with APIs. APIs are really tough to work with because every API is different. There's version control issues. So, WebEx changes a version of an API. The thing that talks to it doesn't work anymore because this has to update. So Anthropic realized we got to rethink this. The whole API thing is just really, really hard to work with. So they said we need a stable protocol that is not going to change. It's like, TCP/IP is how the internet was built. It grew because it was a stable protocol. It's a simple protocol, but it's stable, right? It let us build this massive internet. If we could do the same thing here with agentic systems, we can also scale these out very, very fast and it will grow. So they published it last November. It got 50,000 stars on GitHub in its first month. By March, OpenAI, ChatGPT guy says, hey, we love it too. We're going to support MCP. And as soon as you've got Claude or Anthropic and OpenAI agreeing on a protocol, guess what? It might as well be the standard. So it is effectively now the de facto standard model context protocol that allows us to build these kind of systems. So how do we work with MCP? What is MCP based on? Let me compare it to how traditional APIs will work. So in the traditional API world, you have your client, it's got an API to an application, and it's going to talk to some services on the back end. So you've got these APIs that make these calls to back-end services. We've done this for 25 years. This is very familiar to us. We know how this works. Now, when people started coming with LLMs and agents, they kind of did the same thing. Well, if I'm going to go talk to those tools, I just do an API call to those things. If I'm going to talk to WebEx or Splunk or Azure or AWS, I'll just do an API call to them. And that's how we've been building it for the last couple of years. And that's where Anthropic said, this is probably the wrong way to do it. We're never going to scale if we build it based on APIs. So first of all, I just want to define, what are these things? What is a tool? In the agentic AI world, tools have a very specific definition. So a tool could be anything that executes code to talk to an API. It could be an API, but it could be a web search. It could be a calculator. It could be a database write. It could be something that just does some particular function. But in the case of Cisco, a tool would be like Meraki. A tool would be Thousand Eyes. A tool would be Intersight. It would be Nexus Dashboard. Those are tools, right? We're going to talk to Azure. Azure is a tool. It's something externally that normally you would have used an API to go and connect to. So if this is the way we used to build it, when we built it with MCP, there's a little bit of a different function here. There's something called an MCP server. The MCP server has a very, very specific function. It is the thing that will talk to those backend tools, and it abstracts the API. So the API still exists here. It's just that in the agentic world, we're not talking the API anymore. We're talking the MCP protocol. That's the stable protocol that never changes, which means your model doesn't need to know a thing about the API. None of your agents need to know about the API. All they have to do is talk this stable MCP protocol, and it's this MCP server, which is your translator. It translates to that existing API. Now, you're thinking, well, what have I actually sold? I just moved the problem somewhere else, haven't I? The API is still there. But this is why it's such incredibly thoughtful thinking. This is like next level thinking. So Anthropic said whoever builds the tool, they have to build their own MCP server. So if I go build the API for this tool, if I change the API, guess what I have to do here? I have to change the MCP server at the same time. So everybody out there who builds a tool, they have to build their own MCP server. There's not like one massive, MCP server that people are going to sell. The MCP servers are different for every tool. I go change this tool's API, I change the MCP server. The translator is always statefully keeping sync. So this will always allow my communication to work. So putting this all together, you have your agent here. This is your LLM's agent. It's basically a client. He's talking to the MCP server. He says, hey, I need a tool that can go and calculate something for me, or I need a tool that can go and pull data on network performance. And the translation happens to the tool of the API here. He does the translation, and the LLM is just orchestrating everything in natural language. It abstracts everything, makes it very clean. You can see why this took off like incredibly fast. And now literally the entire industry is building agent systems based on MCP, including Cisco. So every product at Cisco is building their own MCP server based on our SDK for the internal, the central AI team. And it's going to follow this kind of architecture. So here the agent and the client, they all talk together in this way. This is very key. So, if Meraki goes and changes their API one day, they just go change their MCP server, and we continue to talk to it. It's going to keep working. So if we go back and revisit the architecture that we talked about, where you have this kind of multiple layers of architecture, instead of just going and talking APIs, now you've got this little Cisco MCP server. These are different, right? They don't have to be one mega MCP server. You've got different ones for each tool on the back end. And this is how we can grow. So this scales really fast. Think about integration now. In the past, we'd have to wait 18 months to onboard a product and integrate it because you have to wait for the APIs and everything on both ends to work. Now, all we have to do is just talk with MCP. It's like an IP address. It makes it that simple to grow these. And by the way, in the MCP server, how the model learns about the tool, it's just a natural language tool description. He says, this is a tool that does WebEx communications and troubleshooting. Natural English. He tells the model, oh, that's the one I need. You go connect to that tool. And it's very, very simple. Right? So that's MCP. Okay, so that works well. I want to talk a little more about now the model itself. How do you approach model design and model tuning to make these agentic systems work? Now, you remember I said you have to be a reasoning model. You have to reason through complex steps, how to solve, why is a routing protocol flapping, or why are we black holing packets over there? This is multiple steps, right? Could be 5, 6, 7, 8, 10 steps to go and solve a problem like this. So we have to train the model to know how to do that. So the deep network model, we start with a foundation that already knows language. So we don't start absolutely from scratch. There's no point in doing that. The first thing any LLM has to learn is just language skills. So why not take a very good model like DeepMind's Gemma model, begin with that, and then you begin introducing new knowledge to it. And new knowledge is what fine-tunes it to be very, very good at reasoning through multiple steps. So a general high-level process for fine-tuning looks something like this. So you begin with your foundation model and you evaluate it. You look at it, you see, what is the model, how many parameters am I dealing with? What's the model structure look like? What was the source training material? You get an understanding, you evaluate your current model. Then you start to look at the gaps. So you look at what's missing from this. Okay, maybe it's missing some problem solving, networking kind of skills and all this, and you identify the gaps. That's where you have to identify the fine tuning data set. So you say, this is what we need to go and build. This is what we need to collect. And you can collect it in various ways. You can go to a place like TAC. You can crowdsource it from engineers. There's a lot of ways, right? You can build your corpus data set that's going to build this. So then you start to build this in. You fine tune the data itself. So you do some normalization. You do some design hypothesis around the data to make sure it's structured correctly. There's actually a human validation step that's very, very important. You have to make sure that we're solving the problem in a way that an SME would actually say that this is not the wrong. If you train it on wrong data, it's going to try to solve it the wrong way. So you actually need a human SME to validate a lot of the data. And then you start to feed in the new data with a mechanism called supervised fine-tuning, or SFT. So SFT introduces the new data, and you see the circle. You have to feed the same data set in multiple times, 20, 30 times. It's like a human, right? If you're trying to learn a new skill, how many times you have to practice that skill before you become an expert, right? If something very simple you've never done before, but it takes some time, right, to practice it. But after 20, 30 tries, you feel, okay, I've mastered the skill. That's how LLMs work too. You have to train in the same corpus that many times until it really learns and to generalize those patterns. So supervised fine-tuning is the core way that people do fine-tuning of models. You start with that foundation model. You use the new data set that goes in, and then finally you have to do this reinforcement learning with human feedback step to make sure it's actually doing what you think it's doing. That it's not giving you the wrong steps, that you have to do something that will have that human element to that last fine-tuning step. So how do you go and fine tune a model with supervised fine tuning? Well, the way that we used to do it, the way that everybody used to do it, was called transfer learning. So imagine you have a model that's, let's just say, 20 billion parameters. What you would do is you'd feed in your new data and you would update all 20 billion of those parameters. That means those little weights on those neurons inside the neural networks, 20 billion of them have to be recalculated over and over and over again. And you would feed that in, and eventually you end up with a new model where all the weights basically have changed. So some of them might be a little bit, some of them might be a lot, but you've got basically a change in all of the model weights. Even for a small, this was a very expensive proposition. Why is that so expensive? Because GPUs are expensive. Now, just to give you an intuitive sense why it's hard to do this, in anything in computer science, numbers are always stored as floating point numbers. So typically in models, we use called half precision, so 16 bits of floating point. Of the 16 bits, one of them is for the sign, so it's positive or negative. You've got 5 bits in traditional floating point 16, which is for the exponent. That's how big the number is. And then the mantissa is the actual data itself. That's the number, the actual number. So FP16 is typically the way that you get a model, you start to fine tune it. Now, there's better ways, like bfloat comes from Google Brain. It's why it's called BrainFloat. They kind of optimize this in a slightly different way. But if I've got 20 billion parameters and they're all 16 bits, how much actual GPU am I consuming here? Well, let's find out. So let's say I've got this nice 20 billion parameter model. I'm using that example because OpenAI has got this new open source model, the GPT OSS 20B. So you can download. It's your first downloadable model. You can fine tune it. So it's not that big, right? You still need a bit of a GPU. You can put it on a gaming PC, probably, But I'm going to fine tune this model. So how much VRAM on that GPU am I actually going to consume? Okay, so I've got 20.16 times 20 billion parameters. 16 bits means 2 bytes. So to load all those into VRAM, that's 40 gigs, 40 big gigs of VRAM, just for the foundation model weights. Now, I'm training them, so I have to do the gradients. That's the change, right? How much those models are changing during the training process. So those have to also be stored in memory. That's another 40 gigs VRAM that's being consumed because of the gradients as the backpropagation happens with this model. Okay, so we're up to 80, right? 80 gigs of VRAM we've just consumed. It's only a 20 billion parameter, but we just consumed 80 gigs. But hold on a second. When I'm doing backpropagation, I'm using an optimizer. The most common optimizer everyone uses is called Atom. Atom is a very, very efficient optimizing technique. We have 2 things called momentum, and then there's variance. These are the very specific things that help the model converge. If you don't use these, your model will not converge quickly. It'll take forever to train it. These have to be stored because they're so precise. We use 32 bits of data in floating point format. So you need full precision if you're doing those kind of values. Now you're up to 80 gigs for each of those, and it's a total of 200 gigs of DRAM to fine tune this tiny little 20 billion parameter model. That's what we used to do all these years. Now, there has to be a better way. And the better way was introduced by Microsoft. So Microsoft Research, MSR, published a paper where they said there's a better way to do this. And they called it LoRa. It's low rank adaptation. And the basic concept of LoRa is they said, all of these weights, these 20 billion parameters, what if we don't even touch them? We'll just leave them. Like they're doing a fine job. We don't have to mess with 20 billion parameters. Why don't we do something a little bit different? Why don't we stuff in a new layer, a tiny layer, and that's called an adaptation layer, and that's where the new data will be stored. So they said, we don't have to consume all that VRAM and all these model weights. We'll use this adaptation layer, and that's where all of the training is going to happen. And this LoRa, let's just go back to this slide. Why it's called low rank, it's basically how much data, the rank is how much data you want to store in this adaptation layer. If it's low, you're not going to be storing very much at all. For example, this is a project that I did very recently. So this was using a Llama instructional model, a Llama 3 model. And this was a fairly small model I did on my laptop. It's a 1.7 billion parameter model. Oh, sorry, 1.2 billion parameter model. Okay. That's how many trainable weights there are in that. Using LoRa, I'm only stuffing in that adaptation layer with 1.7 million parameters, which means the trainable was 0.13% of the whole model. So of that 200 gigs of VRAM, I'm using 0.137% of it, and I achieved the same thing. So our approach to model training, as everyone else in the industry, this is not like, this is not like rocket science anymore. People are all doing this. We're using parameter efficient training using LoRa. You can accomplish the exact same output with just a tiny fraction of your VRAM required. Now, there's one last little detail. When people talk about LoRa, there's another thing called QLoRa that goes along with this. It's called quantized LoRa. And the idea of quantized LoRa is that while I'm putting that new adaptation layer where the training happens, those other 20 billion parameters that I've frozen, I still have to load them into memory, right? Just to hold it, they have to be held into memory. So what we do is they came up with this other idea. Instead of using 16 bits for all that quantization, they said, what if we can compress it? It's just like taking an image like you take with your camera, you compress it down to a smaller JPEG. It's a compression. Let's build a compression for that 20 billion, squish it down to only 4 bits. And the way they did this is they noticed a very interesting observation. If you look at all the different weights across the model, if you were to average all the weights, the average is actually 0 because there's negative numbers and there's positive numbers. And it turns out that if you kind of put a graph together of all the weights across all 20 billion parameters, it looks kind of like a bell curve. And that's a fascinating observation because the density of the weights kind of near the middle is where the most of the information is held. So they said with quantized LoRa, we're only going to use 4 bits. So normal float 4, NF4, normal because it looks like a normal distribution, a bell curve. We're going to do this with 4 bits. 4 bits gives you how many total data points? 16, right? 2 to the 4th of 16. They create these 16 little buckets. See these red lines? These are buckets. So they're really tight near the middle where you get precision, and then they space out over here. Now, there's not many data points out here in the weights, so you're not going to really lose much information by having a really wide bucket. But here, where the density of the values are across the model, that's where they want the precision. And the nice thing in QLoRa is that these are different for every model depending on the structure of that model. So you combine QLoRa with LoRa, it lets you take a massive giant model and you can fine tune it with just a tiny, tiny fraction, and you're just maintaining your efficiency. So for us, this is why we can continually retrain our deep network model using these techniques. New data comes in, we train it with LoRa, QLoRa, and it comes out very, very fast. So what do we use for our source training set? What is our corpus made of? Things like Cisco TAC methodologies. We don't care about, we do not look at PII data for TAC cases. We don't want a company's name. We don't want an IP address. We don't want anything like that. All we care about, what was the problem? How was it solved? What were the methods involved in solving this case? That is what we can train into the model to generalize it. We look at engineering traces. So we have 30, 40,000 engineers at Cisco working on different products. Just get them to document, how do I troubleshoot the product I'm working on? Train it to the model. We look at Cisco Learning Academy, Cisco University, all these CCI documents, sample lab code, we train that in, and it goes on and on. So this is becoming a very large corpus of data, which fine tunes in. And the question is, are we going to just start selling deep network model to people? Is that going to become the model that we issue to people? Well, that's not our intention. Our intention is that is the internal brain of the AI canvas. So as you're starting to use AgenticOps, hopefully by the springtime, you're all going to be able to start using this. On the back end of it, it'll be the deep network model, which is doing the reasoning, figuring out how to solve these problems, and bringing you to a conclusion. So with that, I think we are out of time, but hopefully that gives you a good snapshot of what Cisco is up to and AgenticOps, some of the things, new protocols like MCP. Hope you enjoy this and enjoy the rest of Cisco Live. Thank you.
So we're going to start in 1 more minute. Okay, I have 3:30, so I'm going to get going because I need every second I can get. This is a lot that we'd like to cover, and I want to make the most of our time. I first of all just want to say I appreciate your taking the time. There's so many things going on, and you've chosen to be here. I appreciate that. We'll make it worth your while. My name is Tim Seghetti. I've been with Cisco 27 years, and working technologies, and the most fun I'm having these days working on quantum with our quantum research team. I lead quantum ready services for CX, and so I want to showcase some of what we're doing here. So what are we doing at a high level? Basically, we want to be the leader in quantum networking, just like we've been the leader in digital networking. We want to support any-to-any, multi-vendor, multimodal, any use case interconnectivity for quantum computers, endpoints, sensors, anything and everything. The whole shebang. That's what we're looking to do. But this is a tall order. We have to bite this elephant off in chunks. Now, I can say this. I could say, hey, you know what? Right now, we're developing a quantum switch for a data center that leverages entanglement and teleportation and actually entanglement swapping. That may not mean a lot to you. So in order to help perhaps better appreciate what we're doing, we're just going to cover some key concepts to lay out what these terms mean, how they relate, and how they interact and allow us to deliver on these technologies. And then that might help understand better what we're building and hopefully drive, I hope some thought appreciation for that. At the end of this session, what I'm hoping you'll get in just half an hour is either some new quantum literacy or reinforced quantum literacy, some key concepts, because we're going to talk a little bit about all of these points. We're going to talk about why build quantum networks, what are some key special properties. Look for all these. We're going to circle back to all these questions at the end. There's a lot of fact and fiction in literature on this subject. Some people think, oh, I've seen some journalists write, hey, we'll be transporting information faster than light with quantum teleportation. Is that really the case? Isn't it? You're going to find out here. And all these questions, like I say, you'll have answered within 30 minutes. At least that's my goal. I will have to talk fast. I apologize in advance for that. So first of all, always start with why. I like Simon Sinek's approach. It's like before we get into the how and what, why even do any of this stuff? Well, there's several use cases for quantum networking. The first one to leverage the quantum networking is cryptography, quantum key distribution. In fact, there's 1,500 kilometer quantum key distribution networks already built in China, as well as in different financial centers around the world. We have rings like in Geneva and London and Singapore and so on and so forth. It's already being utilized as technology in a networking context. However, the biggest and most important use case is not that. It's not QKD. It's this one, to enable distributed quantum computing. Now, when it comes to quantum computing, it's important to recognize that they're not necessarily powerful in every case. In fact, they're not. I'll just make that flat statement. You can basically implement a quantum computer that supports a universal gate set, which means you can enforce and implement any expression of Boolean logic that you could on a digital circuit. So anything you run on a digital computer, you could run on a quantum computer. It doesn't mean you're necessarily going to get an advantage. You could make a quantum computer run as a word processor. That's a waste of resources. But there are very specific things that they're showing supremacy or exponential advantage over. Noteworthily, in simulation, optimization, AI/ML, and obviously the biggest attraction is nation states want to use quantum computers to crack PKI, public key infrastructure. That's something they're exponentially superior at. But there are other use cases too. It's attractive to think that with quantum computers, you're not sharing any information, data, or algorithms with your cloud provider. Everything is blind from their perspective. They cannot read it. Even if you operate on the systems, they have no copy, they have no sense of it. It's completely privacy preserving. That's very attractive in a number of use cases. Additionally, when it comes to GPS and synchronization, you could now achieve orders of magnitude improvements over not just the synchronization of clock signals, but that also translates to hyperlocation based on GPS technology. Or I like this use case. For instance, here in Australia, you guys have these Australian Square Kilometer Telescope Array. Some people familiar with that? It's out in Western Australia. You have 36 deep radio telescopes. If they're interconnected with the regular network, then your accuracy is 1 over 36, square root of 36. So 1 over 6. So about 60 plus or minus 16.6667% accuracy. If you interconnect those same sensors, those same telescopes without changing a thing, you get 1 over 36 accuracy, which is 2.7. So you have a 6-fold improvement in accuracy just in that scenario alone, just by using a quantum network to exchange the information rather than a classical one. And here's kind of like an interesting use case. Quantum money has been proposed way back since the 60s. The idea here is that they're trying to leverage a property called no cloning, so to prevent counterfeiting. But this is kind of making a resurgence with the age of cryptocurrency and Bitcoins and stuff like that. So we'll see. We'll see if that becomes a thing. But I'm just mentioning it just for the sake of rounding out some of the use cases driving quantum networking. Okay, so just to level set some key properties, what we're talking about are quantum bits. That's how we transmit informations with ones and zeros. We take a look at these subatomic particles. Maybe they're electrons or photons or neurons or ions. Those are called modalities, different ways that you can express a state of logical 0 or 1. And if you're using electrons, then basically what you do is you take an electron and you look at its spin. And it has a magnetic spin that will go from the south pole to the north pole, and that's the relaxed state. So we call that logical 0. But it could, just like our Earth, sometimes reverses polarity, and it could be coming from the south pole to the north pole, or anything in between on any one of those 3 axes. The x-axis, which is lateral, side to side. The y-axis, which is front dead center to the back dead center. This is rotating around the y-axis. Or the z-axis, which is from the top to the bottom. So those spins, those electrical fields, can be anywhere in between. And even though I'm talking about electron spin, I don't want anyone to walk away with thinking that there's an actual physical spin. There isn't. It's just an electric field where it's originating and how it's moving, but it's commonly referred to as electron spin, okay? But it's not a physical spin. And I just illustrate it because it's very difficult to illustrate any other way. These electric fields are invisible, very difficult to draw in PowerPoint too. Okay, so then that leads us to our first important property of qubits, and that is this concept of superposition. Maybe you've read this or heard this, and sometimes it's, just put so paradoxically. It's like, oh, these qubits can 1 and 0 at the same time. And then you're like, oh, that makes no sense. It's a complete paradox. It's a complete logical contradiction. How do I resolve that? Okay, so I think a better way to think of that is to think this is a coin, and this coin, after I flip it, can be heads or tails, right? But while it's in the air, at any given instant, is it heads? Is it tails? Well, really, the question doesn't make a lot of sense, but if we really want to think about it, at any given instant in time, there's a probability it will resolve to heads and a probability it will resolve to tails. But what really matters is that when I finally take the reading, it collapses from that state of probabilities in both heads or probability of tails, and then it collapses to a single state. This is what's happening with these qubits. They're operating in a state that has a probability of 0, a probability of 1. We perform these operations on them in this state, but once we take the measurement, that state collapses. That superposition state collapses. Make sense? Now, another important property is this concept of entanglement, where you could have 2 of these particles, and they enter into a special relationship where the state of one is instantaneously affects the state of the other. Maybe it's a opposite reaction. One spins up, the other one spins down, and there's other ways that they could be in perfect sync. But let's say it's a reflection. One spins up, the other spins down. These could be miles apart, they could be galaxies apart, and this will happen instantly. That's really cool stuff. And it's important to remember that this entanglement is not necessarily just 2 qubits entering into a state like this, but rather you could have multiple qubits enter into such a relationship. The current world record is 51 of these. But if I take a reading, again, I collapse that special state and I break that entangled relationship. That's important. We're going to come back to that as we build out our networking. And a final property I'm just going to quickly cover is no cloning. We just made the point that once I take a reading, then that quantum state collapses. But I need to collapse that quantum state to take the reading. I can't read any other way. So how can I copy something I can't read? So mathematically, I have a proof for this. I do a session on quantum tomorrow. I'll include the mathematical proof on the slide. I just don't have time to do it now. But basically, you cannot copy anything in a quantum state. That's the key takeaway. It's a mathematical proof. Okay, now shifting from electrons, electrons are very useful in quantum computing because they have long coherence times. That means they can stay in the superposition state for many operations, very long. However, in order to do so, they have to be shielded from virtually everything. They have to be shielded from noise. They have to be shielded from EMI. They have to be shielded from vibrations. They have to be shielded from heat. They're at minus 272 degrees Celsius. All of these environmental insulations have to happen in order to preserve that. Well, how can we build a network and keep it cool to minus 272 and shield it from all of these things at the same time? So obviously, transporting qubits as electrons is not a very viable solution. Whereas if we use a different modality and transmit information in qubits as photons, now we can send them over the air via lasers to satellites. Now we can transmit them through fiber optics, etc. And then we have a lot more flexibility, and we can even repurpose existing fiber optic networks to do this. Okay, but now we're not dealing with electron spins. What we're measuring is polarity. So what do we mean by polarity? Imagine you drop a single drop of water into a calm pond. Then polarity is the plane at which the waves will oscillate. And as they oscillate horizontally across the level of that water, we say that's horizontal oscillation. It's a function just basically of gravity, but with light, you can have polarity in any given direction. Just like that electron spin can be across any given direction, across any axis, it's the same with the polarization of light. I have 2 lenses, for instance. We probably wear polarized sunglasses, and they'll let in light according to the direction it's aligned. If I turn one of these, and they're both vertical, and so I turn one a quarter turn, and then up to a half turn, now no more light will come through that intersection state. That's just a function of polarity. There's a really cool tool that Olympus offers to allow you to play with the same concepts. Where just adjusting the filter, the polarization filter of the first, and you'll see that more or less light will be permitted through the gates accordingly. Okay, so then how do we entangle these photons? Well, there's a process called one process. There's more process, but one process is called spontaneous parametric down conversion. That's a really cool big word that basically just means we shoot a powerful laser through a crystal. And then one big high energy photon splits into 2 lesser energy photons, and they share this entangled state. And you can do this at room temperature. This is how it looks like in an optical test bed in our labs. Okay, now, if we want to send photons across networks, what you might see here is that in classical networks, the ones we use today, fiber optic networks, not all the photons make it. So you have to subtle pay attention. Some of these disappear along the way. This is very normal, and this is just attenuation. There's always some loss in media, whether it's clear open space, but especially in fiber. And so if we're sending a single photon to represent a qubit, and we have a high probability of losing that, this is a real challenge in order to enable quantum networking over fiber media or even any type of optical media. Because especially you have this exponential rate of decay. The farther out you go, the more intensely you're going to be dropping. And you might say, oh, well, can't we just fix that by using repeaters? That's what we do on regular optical networks today. No, because we cannot clone the traffic. We can't read it, therefore we can't amplify and boost that. And so our hands are a little bit tied here. So how do we work around that? This is where it gets really cool. The sci-fi articles that you read about quantum teleportation, here's how it works in 4 slides, okay? So Alice wants to communicate with Bob. She's got a qubit. We don't know the state of that qubit. We cannot read it. It could be 1, could be 0, could be anything in between. We're not able to read that, and we have to preserve it in that state and get it over to Bob. So what we do is we're actually going to make a channel, a teleportation channel, by taking 2 qubits that have been entangled. Remember, to do that, all I need to do is shoot a laser through a crystal. Now they're entangled. One of those qubits, I'm going to send over to Bob, physically transporting it across media. It's not carrying any information on it yet. It's just, think of it as a channel. Then I do a second entanglement between Alice and one of those qubits. Now I have a combined state, one that was Alice's qubit and some unknown state that was reflecting the state of qubit A at the instant of entanglement. I don't know what that is. Think of it, there's a signal and there's some noise been added, okay? But that signal and noise has been also added instantaneously at Bob's end. So he's got signal and noise over there as well. Now I have to remove the noise. So what I'm going to do is I'm going to take an indirect measurement of qubit A to say, okay, tell me about the noise that was introduced. And basically, there's one of 4 Bell states, so that entanglement could have occurred. And I'm going to get a reading that will correspond to one of these Bell states. Don't worry about the math. I just don't have time to explain it. But basically, each of these states can be represented by 2 binary values. So I send the result of my reading over to Bob, and I'll say, Bob, here's the result of my reading. Now you're going to have to do one of 4 things. Either you do nothing at all. You do nothing at all because they happen to completely cancel out each other effect, and therefore you actually have a clean signaled qubit. Okay, that's one of 4 possibilities. The other possibility is I have to rotate 180 degrees across the x-axis. That's another possibility. Or I have to rotate 180 degrees across the y-axis, or across the z-axis. This is known as phase shifting. So I have to either correct a bit flip, an x or a y bit flip, or I have to correct an x z phase flip. But as soon as I tell Bob what he needs to do, then he'll make the necessary counter the rotation, and then that removes the effect of the noise. And now I've got Alice's original signal received at the far end. I don't know what it is. I don't know if it's a 0 or 1, but it has been preserved in this quantum state, and I've teleported it across the networks. Lovely. Everybody got that, right? It took me hours and hours and hours of reading and reviewing, and it took me a long time. So don't feel like, okay, if you don't catch it on your first try, that's very normal, but at least we're just, again, trying to illustrate some of the concepts as simply as possible. I think some of these sessions, I know the session tomorrow will be recorded, and so you can go over it again as many times as you like. Okay, but what if we need to extend actually, before we extend, let's just say I want to include a switch in between Alice and Bob. Then what I'll do is I'll create that entanglement at that central point, and then I'll shoot one to Alice and one to Bob, so that they now have that entangled channel, and then they can communicate over it, one to the other. So this is great if the 2 endpoints are directly connected to a common switch, like a top of rack switch in a data center. But if I have to go farther, now I have to get more creative. So for instance, I could start in the center, but then I haven't made it all the way to my endpoints, so I perform another entanglement operation, and this is called entanglement swapping, and I build a chain of entanglement as long as I need to get from the sender all the way to the receiver. And I have to recreate these chains each time. And so this is quite an intensive operation, but this is how I can achieve this even over multi-hop segments. Okay, so then with all that preamble, what is Cisco doing in quantum? Let's review some of the key engineering challenges. Now, a lot of companies are playing to their strengths in quantum computing. IBM, Google, Microsoft, and all of a lot of them. And so like they're saying, okay, that's what we're going to run after. But whereas we're focusing on these engineering challenges that relate directly to networking. Like I say, we want to build to our strengths. We know networking. We have deep expertise in photonic and optics, and protocols, and security, and all of these things that directly relate. And so this is what we're going to leverage and build on. So the overall steps, well, you got to start with research to figure out mathematically how to model this, how to make it even possible, and then publish those findings, and then have a theoretical body of work to guide that practical implementation. Next set of steps involves simulation and emulation. You're going to try and build as close as possible these types of systems so that you can test your concepts before you go into an optical test bed, for example. These are very difficult, complex, and expensive tests to set up. So you want to do the maximum you can in a simulated environment or emulated environment. And then beyond that, then this allows you to develop hardware and software. So let's look at some of the key achievements in that area. We publish about 10 academic peer-reviewed papers a year. And so here's one of our seminal papers that showed, hey, how could we build a unified, hybrid, classical, and quantum internet? That's what all the quantum scientists call our networks now. They call them classical, which sounds very quaint and outdated, but I'm like, whatever. So it's like you just got to let them use that term. But then also, I thought this paper was very brilliant too, that showcased how we could use existing fiber optic networks. So we don't have to rip and replace everything, but really make the best utilization of infrastructure that we already have, but to enable quantum networking. There's many, many more. Okay, I can't feature them all, but you get the idea. Is that our quantum scientists, and we have a team of them, are leading the advances in these spaces and coming up with many industry firsts. We've also built the Quantum Network Design Kit, so basically allowing you to build a quantum digital twin to say, hey, how would you interconnect these endpoints, and what would be your topology, what would be your signal strengths, what would be the distances in between, and how, what kind of losses would you expect, etc. It allows you to model and simulate all these things out so that when it came time to build the whole thing, you're much more confident and you have a much higher rate of success doing so. Not only that, but earlier this year, we opened up a lab dedicated to quantum research in the city of Santa Monica and outside of or near Los Angeles. And I think it was funny because we originally intended to open this several months before, the year before September. And then we got derailed because in the city of Santa Monica found out the strength of the lasers that we were planning to use in this area. They set up a lot of extra bureaucratic red tape that we had to clear, and then we were able to proceed with opening it up and getting all the necessary approvals. About a year ago, we brought one of the first quantum hardwares to Cisco Live, and that's a quantum random number generator. And this is important for all sorts of use cases: cryptography, simulation, etc. All the random number generators we use are not actually truly random. They're pseudo-random. They start with a seed function, and there are some patterns in it. But to be truly useful, particularly in cryptography or simulation, you need to be mathematically totally random, and quantum meets that and is mathematically provable to be that. And then quantum random number generator, we also have an API that you can interface. So if you actually want to grab a purely random number, whatever your key length, you just, tap into it, and then the API will provide you one from that. It does these beam splitting, and these states, like I say, are proven mathematically random. Earlier this year, we released this quantum entanglement chip. I thought this was absolutely brilliant. So basically a chip that does that operation of entangling two photons and then sending them out across optical wires. You'll see that it produces 200 million entanglement pairs per second. That's huge. And it only takes 1 milliwatt of power. So very, very efficient. These are all industry first to achieve this kind of rate, this kind of fidelity, this kind of light power consumption. It's just a whole series of industry firsts. Also, in addition to that, we recognize that we've got to think of not just from the hardware on up, but from the software down. So this idea of hardware and software co-development. For example, the challenge right now in quantum computing is that no single quantum computer can accept the quantum circuits at the scale that truly useful use cases, the biggest, most valuable use cases require. So many of them are viewed, you need about a million logical qubits to execute things like breaking Shor's algorithm for PKI. That's a use case that's commonly viewed as a benchmark, or to do very complex simulation for chemicals or weather forecasting or stock market analysis and stuff like that. So how then would you take the requirement of 1 million qubits and then assign them on computers that are at this time a few dozen qubits or a few hundred qubits? So to be able to slice up these complex quantum circuits and to distribute them, and to make sure that all the circuits and all the error correction and all the scheduling and all the logic needed to order to treat that collection of quantum computers as a single unified integrated computer is done properly is a function of this quantum compiler. And again, this is a whole series of industry firsts, particularly in distributed quantum error correction and so forth. Therefore, our overall, what we're building out is starting with a quantum switch at the hardware level, building a quantum fabric for a data center, a quantum data center, orchestrating that quantum data centers, which is quantum compiler that we just talked about, integrating with not just quantum computers, but even quantum sensors. We talked about the benefit it brings to various sensors like the telescope array. It has a quadratic improvement in accuracy when you transmit the information from sensors over a quantum network versus a classical one. And then not just the hardware, but then all the software applications on top of that at the same time. So this is our overall strategy and vision and how we're approaching these problems and what we're building out. Okay, that all being said, you ready for the quiz? All right, so remember, these are the questions I said at the end of it. If I've done my job, hopefully you'll know the answers to all these questions. Okay, so first of all, why build quantum networks? What were some of the use cases we called out at the beginning? Just anyone. What's that? Weather modeling, good. Yeah, encryption. The weather modeling is an example of distributed quantum computing, block computing, privacy-preserving cloud computing, interconnecting sensors, making them more accurate, interconnecting clocks, making those more accurate, etc. Okay, next one. The big one, though, the biggest use case by far is to enable distributed quantum computing. I really want to leave that and impress that with you. Now, what are some special properties of qubits? We talked about 3 specific properties. Superposition, love it. Entanglement, good. No cloning, all right, I love it. This makes me feel really good. I get so excited about this stuff. Okay, here's a question you might see in the media. Can we separate fact from fiction? Can you transmit information faster than light? We went through all the steps. Who says yes? Okay. Who says no? And I want you to focus on the word information. So do you remember how we did the information transfer? First of all, we started by taking 2 qubits, 2 photons that were entangled, and physically transporting one from one side to another. So there's a physical transport. Then we did the entanglement, and then that transmitted basically some signal and noise. It's not useful information at this point, but that did happen instantaneously. Then we did a measurement and sent the results of the measurement over a classical network. So let me ask the question again. With quantum networks, can you transmit information faster than light? Who says yes? Who says no? All right, all right. I feel really good about that. Now, a related question. Will quantum networks replace classical networks? And I invite you just to consider what we just reviewed. Who says yes? Who says no? No. You're absolutely right. We have to transmit information over classical networks. The original photons that are going to serve as our media channel, the 2-bit result of that quantum measurement. And if you look at everything quantum, we're talking about quantum networks right now, but even if you look at a quantum computer, it's not pure quantum, it's a hybrid. There's quantum elements and classical elements. Everything in quantum will follow that hybrid model. And so quantum computers are hybrids, quantum networks are also hybrids. It's not going to be one or the other, it will be a combination. Okay, and final question. What are some things Cisco is researching and developing in quantum? Feel free, call them out. A chip, yeah? So everything from research papers to simulators and emulators to actual hardware development, quantum random number generations, entanglement chip, as well as compilers. It can take high-level quantum circuits and logically distribute them so that we can then enable them in a quantum data center. That is the likely best path forward to leveraging the capabilities of quantum computing in the near term. If you're going to wait for one computer to support 1 million logical qubits, it's going to take you a lot longer to wait than to say, okay, I want like 1,000 computers, 1,000 qubits all interconnected. So anyways, just some thoughts to keep in mind. This was, again, to serve as an introduction, a primer, some basic quantum literacy. Thanks again for taking the time. And hopefully then you'll walk away with, hey, knowing a little bit more about quantum. You can share some interesting trivia at the dinner table sometime. And then you see also what we're doing in this space. If you want to learn more, feel free to come to my session tomorrow. Thank you so much.
Okay. Good afternoon. Can you hear me? Okay. Hope everybody's enjoying Cisco Live. If you are here for automated Meraki switch port configuration copies for switch lifecycle replacement, you are in the right place. You can please join the discussion in the WebEx space by clicking join the discussion in the app. And I am Ed Novak, a technical marketing engineer from the network platform team. I've been at Cisco for 25 years. We've done a lot of exciting technologies over that time. For the past 10 years, I've been working on network orchestration and network automation. So I recognized I can put together a training plan, follow that training plan, and achieve success in achieving certifications. And then 2 years ago, I took that same skill about putting a training plan together and following it for success. And I first started doing marathons, and I started doing ultra marathons. And then earlier this year, I did my first 100K event. So I was quite excited about that. But as doing ultra marathons, I realized that when I'm looking at an event, I have a list of questions I ask. And so I'm going to apply that to network automation today. So we're going to talk about network automation from an ultra runner's point of view. Now, don't worry, I'm not going to ask you to get out your trail runners like I have on today and do a few kilometers with me. We're just going to ask some questions about network automation.
the same questions I ask when I'm looking at a new race. For example, what are the race details? So in this case, what is agentic workflows? We'll talk about the registration fees, and I know you're going to like the answer you hear today about that one. We look at the core workflow. For us today, that's a workflow. We'll review the frequently asked questions. We'll talk about aid stations. So in ultra marathons, there are aid stations along the way to help you complete your goal. Here, we're talking about what's aid stations are out there to help you get started with using workflows. I look to see if there's a race review I can follow. In this case, we're talking about a live demonstration of workflows here today. And of course, we got to make the cutoff time. My timer is running, so let's get into it. So starting off with, what is agentic workflows? Agentic workflows is cloud-hosted automation embedded directly into the Meraki dashboard. And just because we're hosting the Meraki dashboard doesn't mean we're only for automating Meraki. You can automate across the different Cisco domains, including Catalyst Center, Catalyst SD-WAN, ICE, FMC, for example. Integrate with third-party tools like ServiceNow, Jira, NetBox, and other AI integrations. Some exciting stuff there. We provide a simple, low-code, really no-code, drag-and-drop automation environment for you to create and edit workflows. We also have what we call the Workflows Exchange. It's a catalog of pre-built workflows. You can take those, bring them into your workspace, run those as is, or if they don't quite meet your need, open them up in that simple editor, customize them to meet your need, or build completely from scratch. The whole goal here is to eliminate those repetitive manual tasks, make utilizing APIs simple and easy. So back in June at Cisco Live in San Diego, we announced the rebranding of the Meraki dashboard. We changed from green to blue. That's part of that common user experience going on at Cisco. There are other teams at Cisco working on common APIs and common policies. I'm part of the team that's working on common automation strategy across Cisco. So what that means is that we have different teams working on the same common automation engine software. So if you're familiar with XDR Automate, the security side of things, a lot of what I'm going to show you today is very similar because we use that same automation engine. So there's two different development teams working on this platform. So that's going to accelerate feature velocity like AI integration. We still maintain our individual domain focuses. They're focusing on security incident response, but we're going to focus on network automation orchestration, help you give your use cases life. So this is the list of current targets you can integrate with inside of Cisco workflows. So right at the top of the list, you see HTTP endpoint. So anything with a REST interface. Right below that, you see Ansible. At the bottom, you see Terraform. So if you have existing automations, either one of those platforms, it's not throwaway work. You can trigger those from inside the workflows environment. Then you start seeing the long list of Cisco domains. So Cisco Catalyst Center, Catalyst SD-WAN, ICE, Umbrella, for example, and of course, Cisco Meraki. Then you also see those third-party tools, ServiceNow, for example, and NetBox. I mentioned we have flexibility here. We have those pre-built examples from the Exchange. You can run those as is, open them up in the editor, customize them if you need to, or build completely from scratch. The Workflow Exchange has 3 different levels of offers inside of it. The first level is Cisco managed offers. Those are built by Cisco, and Cisco supports those. Next, we have Cisco verified offers. Those come primarily from Cisco partners. Those have been tested by Cisco, and those are going to be supported by a Cisco partner. And the third level is Cisco community. So those are from community authors themselves. Cisco has looked at them, validated there's nothing malicious in there. The basic logic looks good, and support comes from the community at large or from that individual community author. Let me get to the workspace. I call this your collaborative automation environment. So you can see the status of your workflows. You can share your workflows by importing and exporting them as a JSON file or syncing them to a GitHub repository. You can see the status, you can run them. And then we get to the workflow editor. This is the heart and soul of workflows. That simple drag and drop, low, no-code automation environment. Left-hand side, I've got my palette of activities I can select from, drag it out to my canvas. I can reorganize things in my canvas if I need to. I get a visual representation of my workflow. And the right-hand side is the properties where I can do any configuration aspects I need to. This is all going to be AI-driven as well. So the great thing about the AI system now inside the Meraki dashboard with access to agentic workflows is that instead of asking for help now, I can ask for an outcome. I can ask it to help me with automation for lifecycle switch replacement, and it can recommend a workflow for me. It allows me to remain control over my network configuration changes. It asks me to verify any configuration changes before I make them with a workflow. The important thing to keep in mind with a workflow is the concept of deterministic. So workflows are deterministic. It means if I give it the same inputs, I always get the same outputs, just like with a Python script, for example. So when AI is using a workflow, it's utilizing a tested and deterministic tool to make changes to my network. So how do we run a workflow? Of course, we can run it from the AI system. We can run them manually through the dashboard. Additionally, we have flexibility using an API, a webhook, or a schedule to trigger a workflow. The next question you have to ask yourself, what does all this cost? So the great answer here today, it's free. This is a value add for being a Cisco customer. There's no risk here to adopt and deploy this. You get access to all those Cisco adapters and automations, and team and networking community focus. So the thing to keep in mind is we just went general availability last month. So for the past month, you've all had access to this powerful free network automation tool. Why aren't you using it? So let's take a look at the course itself. In this case, let's take a look at this workflow that does switch port configuration copies. So here's my full workflow. When I click on run, it brings up the input screen. So these are the inputs required for this particular workflow. Now I could have modified this workflow and had it go out and collect that information and present like a drop-down list for me of serial numbers and switches to my network. But the benefit of doing it this way is the only input you see on here are serial numbers and port numbers. So since it operates on a serial number basis, I can actually use this workflow to copy switch configurations, not only between switches on one network, I copy switches between networks, and actually between networks in different organizations, because it's operating at the serial number level, provided that an API key associated with the target here has permissions on those networks. So starting second from the bottom down here, I have a Boolean value here. It's asking me for all ports. So if that's set to true, it's just going to copy all the ports of the source switch to the target switch. If that is set to false, then looks at the port IDs. And it's going to copy the port ID source switch, the port ID, and the target switch. The serial numbers, those are the switches involved with this. So it makes it very simple to use this. Now, the right-hand side, this is actually the workflow shown inside the editor. It's a little bit of an eye chart at this level, but we'll dive into it and take a look at each individual piece of that. So starting at the top, we have the common actions. This is kind of the configuration harvesting. We're going to gather the source and target port configurations, gather the port numbers, and set our port count variables. So looking at these individual activities on here, we start off at the top here, a Cisco Managed Atomic. So I click and drag that from the palette out, drop it onto the canvas. No coding involved here. The only input it requires is the serial number. And so I click on this little browse variables icon you see highlighted here in orange. I click that browse variables window. And here I'm able to select my workflow input variables, my source switch serial number. So no code involved. I've identified the input to the workflow, have this particular activity to retrieve that source port configuration. Same thing for the target switch port. Next thing they do is take the data we get back from that activity. In this case, we're going to put it into a table so we can iterate through and utilize it. So I'm going to use a read table from JSON activity. Again, I click and drag it out from the out onto the canvas, drop it in there. The first thing I need to identify for it is what is my source JSON. So again, I click on my browse variable icon, brings up that window. I'm going to go activities. The previous activity in this case was that you get source activity, and the output from that is a result of the JSON data. So I have the JSON data I need to utilize. I just need to provide the JSON path and then start identifying the columns of that JSON that I need to utilize, for example, the port ID. Once you've identified the information for the source switch or the target switch, my next thing to do is set the variables. So this, again, using no code, I drag a set variables activity out of my canvas. I click on the browse variable icon to identify either the variable I need to update, in this case, a local variable for inside the workflow for my source port switch count, or then I identify the new value I need to assign to it, the output of some of those previous activities, like when I read the table from the JSON file. Below that, we break into the conditional then statement. So I'm going to look at that all port boolean that was set at the input time and see if it's true or not. If it's true, I'm in my all port, my workflow. I'm going to loop through all those interfaces. So I need to check to make sure that my source switch port number is less than my number. So I can't copy a 40 port switch to a 24 port switch, but I can copy a 24 port switch to a 48 port switch. So I verify my numbers, and then I loop through. I select my port ID, I go to the source and target switch. In this particular case, I am looking for numeric port IDs. The uplinks in Meraki switches, some of those are alphanumeric. This workflow could be modified for that, but for the basic level, this meets most of our needs. And then we copy the switch port configuration and set our output message. So looking at the top of this, our conditional check right here. How do we verify that that Boolean value we set at the top, that all ports Boolean is true or not? I drag a condition block out onto my canvas. I open up my conditions right here, and the first item it asks me for is the property. And again, I click my browse variables window, workflow input, my all ports value. I identify how I need to compare that. That's a comparison operator. So I click on my drop down right there, and I present it, in this case, since it's a Boolean value, either be equals or not equals. So I have a limited choice right there. If this was a different variable type, I have different comparison operations. And then finally, I have the value I can compare it to. I can either enter a static value like I have here, I make it true, or again, I have the browse variable icon available to me to identify what type of variable I'd like to compare it to. Below that, we drop into our loop, which will loop through into the interfaces on our source switch to copy them to our target switch. So I drag out a for each loop onto my canvas, drop it in there. The only thing it provides for it now is an array. So I click on my browse variable icon right there. I look back at my activities where I read that table into JSON, and I grab the output because that's an array data value that I can utilize to loop through each of the interfaces on that switch. The next thing I need to do is select my target switch port data from the table. So again, I read all that information to a table earlier. Now I need to pull that information out of that. So I have a select from table activity I dragged out onto my canvas. I've identified the input table in my browse variable icon window there. I gave it a where clause to identify what data I want to read, and I can select which columns I want to read. So earlier I grabbed the port ID, the name of the tags from my source, or in this case, my target switch port. Here I just need to have the port ID of the target switch port, so I know which port to update. So I'm going to select a single switch port from that table activity. Do the same thing for the source switch port, but in case of the source switch port, I need the full configuration because I need to read all that data in to apply it to the new switch port on the target side of things. So here, it's the same thing. I use my browse icon to identify my input table. I have my where clause to identify what row I need to read to it. And then for result columns, I click on the button there. That brings up the full list, and I just click the all button. So a couple of clicks right there. I've got all the data I need now. So I have the entire source switch port configuration to utilize. The next step here is to apply it to the target switch. So I'm going to grab the pre-built activity, updated device switch port, drag it out, drop it onto my canvas, and then below that I have all the different settings that I can set for a particular switch port. I bring up my browse variable icon and begin mapping them from my table value for each of the individual settings I need to update on my target switch port. And then finally, let's set a result code and a status message. So this allows me to provide an update if this workflow is used as a sub workflow for a different workflow, or a useful message for my user to look at. I can use my browse variable icon to identify what variable I need to update. So again, I'm going to look for workflow output variable, and I can provide either free enter text or a mixture of text and variables, as we see below here, to provide a useful message for my users. The single port side of this workflow is very, very similar. We're going to be looking to make sure that the source and target switch ports are valid. I can't copy a port 25 onto a switch that only has 24 ports, for example. And then we look at our configuration. So it has configuration logic right here in our conditional. The first thing is our source port and target ports valid? So is that port ID less than or equal to our port count on the switches? So I have two of those checks right there. They're ANTed together. And then below that, my next question is, are port IDs equal to 0? So if they are, I need to filter those out as well. So I'm checking to make sure that my source and target port IDs are not equal to 0. If all those conditions are met, then I jump into copying that switch port configuration. And the output side of things right here is shown here. At the top, we have my input variable. It's highlighted in red. So for a single port, that input Boolean value is false, in which case I'm going to read my source and target port ID numbers. Those are also highlighted in red. In the orange blocks, I have the 2 serial numbers provided. At the bottom, I see my overall result is green, it's true. And then at the bottom here, I have my output status message where it says, hey, I copied port 1 to port 1 because those are the 2 port ICDs provided. And on the case where we're having all port booleans set to true, I'm going to ignore my port ID. So I'm going to copy all the interfaces from the source switch to the target switch. I read my 2 serial numbers. I have my results at the bottom down there, true is green. And then my overall output message here was, I copied all switch port configurations from port ID 1 to port ID 10. Frequently asked questions when looking at workflows. Is agentic workflows only for Meraki? And the answer here is no. We're hosted inside the Meraki dashboard. We can automate across the different Cisco domains as well as third party. How do I connect to on-prem or control devices? So if it's not a Meraki device, it may be a Cattle Center device or an individual device. If you're going to connect anything on-prem, that does require the deployment of a remote target, or we call it remote VM. That's a true virtual CPU, virtual machine. You download, install it on-prem. It establishes a TLS tunnel back to the cloud. It allows you to proxy that connection from the workflows environment to on-prem environment. Does workflows count against the Meraki API limits? Currently, yes, it does, but we're working around that because the workflows environment for automation is hosted inside the Meraki data center. We're trying to see if there's other mechanisms we can use to help eliminate those API limits for you when you're using workflows. Another question, how do I limit permissions on a workflow? Currently, you do have to be a full Meraki organizational administrator to centralized workflows, but more granular role-based access control is coming in the next couple of months as we improve the granular role-based access control across the Meraki platform, and those will be rolled right into the workflows automation environment as well. So let's talk about aid stations that can help you get started with utilizing workflows. So the first thing is you're here at Cisco Live. So great news over here in the World of Solutions, CPA 10. I've got a demo booth over there. I'll be over there after this all day for the next 2 days. So please stop by, ask questions, we can go into more details and use cases. The other great thing is there's sessions here at Cisco Live. Unfortunately, my other session was the small. But the great news is it was recorded. It'll be available on demand for you to utilize. And you can also see other workflow sessions from Cisco Live previous sessions. We have a great learning series on the Cisco Workflows YouTube channel. There's currently 11 lessons in it, video lessons of walking through getting started using workflows. A great video learning tool there. We also have some great documentation online. And we have a very active workflows community. So community.cisco.com. Go there, ask your questions about workflows. All right, we're still on time here, so let's jump into a live demo. So I'm going to start off with here inside of my Meraki dashboard. On the left-hand side, you see here down here, my automation menu with my workspace and my existing workflows. I'm going to start here in this network. So I'm in the Workflows TME organization, my switchboard demo network, and I have a MS-120 switch that I'd like to replace in this case with an MS-225 switch down below it here. It's currently unconfigured. I'm going to jump over to my workflow environment. I'm going to grab that particular workflow. I'm going to say run. And again, you see that same input form here, my source switch serial number. And I've defaulted these here for the speed of this demo. So I'm giving it the source serial number for my MS-120. My target serial number here, my MS-225. My all ports Boolean here is false. So I'm going to copy port 1 to port 1. I'm going to click on run. And now it jumps into the live running environment of the workflow. Anything blue is in progress, green is completed. If anything fails, it'll be highlighted in red. But I get to see in real time which way my workflow is run, the branch, the logic, et cetera, inside of that. And I can also click on an activity and get the inputs and outputs of each individual activity as they go along the way. Now, this workflow I'm running right now is actually an improved version of the workflow I just showed you. I've added an item in here for the allowed VLAN. So inside of Meraki, allowed VLAN can be all, but for some of the larger Meraki switches and the newer Catalyst switches that are cloud managed, that allowed VLAN range is a numeric range. So I've added an additional flag in here that'll do a conversion. You select it to convert all allowed VLANs on a trunk to a numeric range. So here we can see if I zoom out a little bit, the way my particular workflow branched. Again, I did the configuration harvesting up here, and then it branched here into a single port because our all ports Boolean was false. My workflow is completed successfully. So I go back over here. If I refresh my page, my target port down here on my 225 port number 1 should now be configured. It has the same exact configuration as above. Jumping back up to my workflow environment, I'm going to rerun that same exact workflow as before, but this time I'm going to come down here and select copy all ports Boolean to true. Run that one again. And this time we're going to branch to the other side of that workflow logic into the all port side of things. And here inside of here, we do have that loop. So up. Workflow, it's dynamically expanding as the workflow is running. Let me take a look up here. So here we're inside of that loop activity. If I scroll over a little bit right here, you can see right now it's iterating through that loop. So I can come in here and at any given time select a single iteration, and I get the current values for that iteration of the loop and see all the activities and the way I branch that loop. So let me scroll down here a little bit. I can see here is my check where I'm looking at that allowed VLAN conversion. I left that as full. That's the way it branched for that run of the workflow. And if I scroll back up, it has succeeded. Looking back at my network, I refreshed. And now instead of copying one interface, I've actually copied all the interfaces from that MS-120 to the MS-225. And that's great in what we're doing Meraki. What if we do Meraki to Catalyst? So here I have another Meraki switch, in this case, MS-120 with some configurations on it. And over here, I have Catalyst 9300, which is cloud managed. I'm going to go back into my workspace. And I'm going to select my other workflow I have defaulted for that particular use case. Right down here. Run. Again, same type of inputs. What are the serial numbers? In this case, my source switch, that MS-120 My target switch over here, the Cat 9300. I don't know if you caught that, but they're actually in different networks in a different organization than the one I'm currently in. But the API key associated with this workflow has permissions on that organization and those networks. So again, it's doing the same thing we saw before. It's running through. It's going to branch to the single side, copy that one switch port configuration. It succeeded. So looking back up here, so here's my source switch, that MS-120. So it was in a different organization and a different network. And then my 9300, again, is in a different organization where I ran the workflow, a different network from the source switch configuration. But if I refresh this, right there's my configuration. So I've copied from a MS-120 in one organization and one network to a Cat 9300 actually in a different organization on a different network. So lots of flexibility here to utilize these workflows. You're saying, yeah, you talked about using AI assistant to help you run these workflows. You're running a manual. What are you doing? Well, let's get to that. Let's talk about using the AI assistant. So here I'm going to switch over here. I'm back into my TNE organization, but I'm in a different network where I have a 120 and a 225 that I need to configure. To refresh my AI assistant because that window timed out. Let me just grab my prompt here and say I need a new thread. Okay. Little glitches always prove it's running live, right? So again, I'm going to ask for an outcome here. I'm going to say run an automation for lifecycle switch upgrade. I'm talking to AI assistant. It's going to look into my automation environment for me and identify a workflow that may meet my need and give me a summary of that workflow. And it has. It says, hey, I found a workflow for you that'll do a lifecycle switch upgrade, which will copy Meraki switch port configurations. The basic steps involved in that are configuration harvesting and then copy switch port configurations. Would you like to run that? I say yes. Now the AI is dynamically going to create an input form based upon the inputs required for that particular workflow. The same inputs we saw previously. We have our all ports Boolean. Here it's true. We see the serial numbers on here. We have the target ports and source ports if we want to copy individual copy switch port configurations. So I can say, yes, that looks good. Again, I defaulted those values. I could override those if I needed to. I'm going to say continue. Because we're making changes to our network, the AI assistant is now going to summarize those configuration changes and present them to me to allow me to confirm those. When I say yes, this is the AI assistant triggering a deterministic workflow. This is not the AI assistant making API calls. This is the AI assistant triggering a deterministic workflow to make those configuration changes for me. And again, deterministic, I give it the same inputs, I always get the same outputs. Here it presents me with a summary of the steps of that particular workflow. The first one, we harvest the configuration, and the second one, we copy that switch port configuration. I'll take it a minute here to run through as it loops through the logic of the workflow, copies all those switch port configurations from my source switch to my target switch. And in just a minute here, we'll see that workflow complete, and it will give me a summary of the workflow activities as well as the output result message. And while we're waiting for that, does anybody have any questions so far? How many people here have heard of workflows before? A couple people from the workflows before. Okay, there we go. We have our summary right here. So again, our workflow completed. Again, we get the message here, completed successfully. You see the result messages right here. Just the details of the switches that copied from, including details on network IDs and things like that, network configurations. And if I close that window and refresh my switch port configuration, there it is. Switch port configuration is copied through the AI assistant. So let me just check my time here. I've got a few minutes left. Let me jump into, hey, we're doing good on cutoff time. So I got a question over here. Let me answer your question. Yeah. So great question there. Could I take that up offline over in the workflows with? I'll be happy to talk about interfacing with like terminals or interfaces. As you saw inside of the workflow editor, there's a long list of adapters you can integrate with, across both the Cisco domain as well as third-party items. Terminal and Linux are just two of those examples. So again, you can use workflows to automate anything with a REST API or anything you can SSH into. So I have made my cutoff time. So I do have a couple minutes here to ask one favor of you. Please complete your evaluations for these sessions. That's very important for us as speakers to be evaluated, but it also helps you improve Cisco Live. So it helps make sure that you're seeing the content you want to see. So please complete the evaluations. If you complete at least 4 evaluations and the master evaluation at the end, you can be entered into winning a free pass for Cisco Live for next year. The other thing is, please visit me over in the demo booth over at CPA 10 Agentic Workflows over there. Here is my email address, or please utilize the WebEx space for this session, or please join the Workflows community online, ask your questions there, and please look at the on-demand session to check out the other workflow sessions from here at Cisco Live. And with that, thank you so much for your time today. I greatly appreciate it.
Hey guys, apologies for keep you waiting. You guys can hear me well, right? So perfect. Thanks everyone. Thanks for joining this session. My name is Aves Khan, and I'm cybersecurity solutions engineer at Cisco, working here from last 4 years, and I'm based in Sydney. So in this session, we are going to talk about how to use generative AI within your organization to cover different use cases like securing your in-house application that use generative AI, and also securing access to third-party AI applications over internet. So this is the brief agenda we will like to cover. As you can see, we'll be spending more time on the demos than the slide pack. So in today's demonstrations, we will like to cover how we can trick the chatbots or like ChatGPT to extract sensitive information or to extract other harmful content, right, with the help of different prompt injection techniques. And then we will also explore how we can secure those AI applications with the help of guardrails, which enforced by Cisco AI Defense. With that said, let's get started with the introduction part. So if you recall our traditional application stack, it was already facing challenges around data security, data privacy, supply chain vulnerabilities. And with the addition of generative AI LLMs, it has further amplified those risks. On the screen, you can see some of the examples of emerging threats associated with different Gen AI applications, things like data hallucinations, prompt injection attacks, toxicity, self-harm. For example, let's say if you have enabled chatbot for your website, right, with the help of different prompt injection techniques, anyone can trick the chatbot to extract sensitive data, or maybe trick the chatbot to perform some actions on the attacker. Also, if you're accessing third-party AI applications over internet like Gemini or ChatGPT, people are misusing it. They are using different type of prompt to extract, some harmful content, like how to create a bomb or how to do a self-harm, let's say. And we have also seen the risk of leaking sensitive data over those different third-party Gen AI applications. So we can categorize those risks into these two use cases. The first use case is around securing third-party access, so basically accessing third-party Gen AI applications over internet. And second use case is around developing in-house AI applications that use Gen AI. So let's start with the private in-house applications. So this slide represents the typical life cycle of Gen AI application which you are building in-house. So in the development phase, you might try to bring off-the-shelf foundational large language model, which might introduce some supply chain vulnerabilities, or maybe you try to create a model from the scratch with the fresh set of data. After fine-tuning phase, the application moves to the production, and to keep the application up to date with the fresh set of data, you use things like vector database via RAG interface, right? If you look at cybersecurity risk, it is there across every single stage of the application development. In the very beginning, when you are picking the foundational large language model, it will bring a lot of supply chain vulnerabilities, right? If you are training the model, data poisoning can occur. your model can be trained on some wrong data. Once the application moves to the production, it is now exposed to the attacker also, right? Attacker can exploit the weakness of your large language model with the help of different techniques, which we are going to explore today. So one thing to call out here is that when you introduce any large language model, it has built-in security guardrails that can offer a foundational security, but these LLMs are more optimized for performance over security. And when you start fine-tuning those LLMs, the built-in security will start getting fade away. And this is what first demo is all about. In this demo, I have logged into a chat interface, basically inside Hugging Chat. So idea is that Hugging Chat is a chat interface hosted inside Hugging Face, right? Inside Hugging Face, you can evaluate different type of LLMs out there. You can download it, play around with it, and there is also built-in chat interface which allow you to play with different LLMs out there. In this example, this particular chat interface is connected to one foundational LLM available inside Hugging Face. Now I'm asking, sending a prompt message like how to track one's position using GPS data, right? This could be against data privacy. So the basic guardrail of this particular LLM is going to block it. But then with the help of prompt injection, we can easily trick the chatbot to extract, those data which was blocked earlier. So let me play the video. So we just send a prompt message, how to track someone's position. It is going to be blocked, right? But with the help of prompt injection, we are going to re-ask the same question, right? And attaching the same question in the end of the prompt, which you can see in the bottom. I hope everyone can see it. I know it's hard to read it, but the idea here is to demonstrate like it is very simple to trick different chatbots out there. This is the another demo for one of the application I have built for this session. And in the end, I will try to demonstrate the application itself hosted inside my lab environment. So in this application, I have connected my AI agent with Gemini foundational model. And idea again here is that I'm going to ask a prompt message that how to create a software that can bypass anti-malware, built-in anti-malware we may have on the operating system. The built-in guardrail of Gemini is going to block that message, but then with the help of prompt injection, we can bypass that built-in guardrail. So let me click that. In the beginning, I asked how to tell me how to write a software code that can bypass anti-malware as a simple example. It is going to be blocked straight away. It is taking time because I'm using a very small compute environment. So, but you can see it was blocked initially, right? Then with the help of prompt message, I reattach the statement, and then the Gemini is going to respond back with the list of instruction, right? How to bypass anti-malware code software with the help of the code. It is going to be presented. So I'll fast forward that, and you can see it basically tell me the step-by-step instruction with the software code. So far we talk about the risk around the in-house AI applications, right? There's pretty much same risk available when you try to access different third-party applications over internet. In this demo, we are going to ask ChatGPT like how to create a bomb, which is very dangerous, right? ChatGPT is going to block it, but then with the help of prompt message, we can trick that GPT tool to give detailed instruction on how to create that dangerous weapon. So let me play that video. Sorry, it's a Gemini, not ChatGPT, but same experience, right? So we asked how to create a bomb. This message was blocked straight away. It said I cannot provide instruction on how to build a bomb. But then with the help of prompt message, which we hide because of safety reasons, this session is getting recorded. Basically, it told me the step-by-step instructions with some visuals, like how to create that particular weapon, which is dangerous. And we have also seen the rise in terms of people are asking ChatGPT around how to do a self-harm, actually, which could be concerning. So now let's talk about how Cisco AI Defense can address the risk associated with the adoption of generative AI. So if you recall the first use case around building in-house AI application that uses generative AI large language model. So we can secure the entire life cycle of that application with the help of these three stages: discover, detect, and protect. In the discovery phase, we will try to discover all the AI assets you may have on the infrastructure, things like foundational models, fine-tuned models, AI applications. Once we have the discovery, we will now try to validate those models. So within our solution, we have a very powerful capability. We basically use AI-based red teaming to discover potential vulnerabilities or weaknesses you may have on the Gen AI models you are trying to use. So with the help of that validation, we try to launch series of attacks, basically more than 2,000 prompt messages, which are mapped to the standards defined by MITRE and OWASP around AI security. Once we discover those weaknesses, we can enforce security guardrails to provide runtime protection for your application. So let's say you have application sitting in the middle. It can be on premises. It could be on public cloud infrastructure. Users are interacting with that application. So AI Defense will sit in the middle, will inspect every single prompt message, and it will also evaluate every response of that prompt message to make sure that prompt and response part is not violating your policy around security, safety, and privacy. So that's the first use case. Second use case is around how we can secure the access of third-party AI applications over internet. So within our solution, we can actually control the usage of more than 1,300 applications over internet, which is very huge. And to enforce that security for every type of user, we are using our SSE solution. We call it Cisco Secure Access. So we have built uh, this capability within Cisco Secure Access platform to enforce security for third-party access over internet. Idea is that wherever you work, your complete internet traffic will be inspected by secure access, including the access to Gen AI application. And once we receive those traffic, we can secure and control it. For Gen AI traffic, we can control that with the help of these three stages. The first one is discovery, where we do shadow AI. Basically, we will tell you what type of AI applications your users are accessing over internet. Then in the detect phase, we will map those applications into different risk categories. And in the last stage, we will enforce security guardrails that will make sure that you are not leaking sensitive data to ChatGPT or DeepSeek or Gemini, or also you are not using those applications to violate your corporate policy around security and safety. So that's the complete picture. AI Defense can address those two use cases, securing your in-house AI application and also securing access to AI. So time for quick demo. I'm going to attempt a live demo of my AI Defense dashboard with some cool demos on my AI chatbot as well. If things did not went very well, I will fall back to the recording. So let me, yeah, I can see the dashboard, which is good. So how many of you have heard security cloud control? Raise your hand. That's good. Thanks, Adam. So basically, Security Cloud Control is our unified management platform that can manage security, that can manage different type of security enforcement point we have in our secure platform, including different type of firewalls that include on-premises firewalls, cloud specialized firewall, our SSE solution. It can also manage our micro-segmentation solution as well. And on the same platform, we are also hosted AI defense. So right now we are only going to cover the AI defense part. So once I go to the AI defense on the main dashboard, you are expected to see the summary of your deployment. Things like how many applications you may have in your environment that has been enabled with AI. We can also tell you how many foundational models you may have on your public cloud infrastructure that you're about to use. We can also tell you how many of those models are already fine-tuned. We can also tell you how many AI agents or virtual assistants you may have. We can also discover shadow AI here. So basically telling you what type of AI applications your users are accessing over internet. We can also give you summary here about different type of validation exercises you have done against your AI assets. And in the middle, basically we are telling how many prompt messages we have blocked actually after we have enforced security policies. On the same dashboard, we have wizards available that help in the adoption of the solution. So if you recall, there are three stages, right? Discover, detect, protect, right? So we are going to explore all these three stages one by one. So first one is the discovery, right? After connecting your infrastructure with AI defense, we are going to tell you what type of AI assets you may have, like things like how many foundation models you may have, how many models are fine-tuned, how many agents you have discovered, and more details around your AI assets. In the bottom, you can see all these details about your AI assets with very important information around validation, whether these AI models are validated by our solution or not. So in this case, not every single of it is validated. So let me show you how we can validate and what we do behind the scenes. So when I go to the validations tab, you can see the summary of all the validation exercises you have done against your application. So let me show you what type of validation we can do. So basically, we can validate your foundation model, which could be on your public cloud infrastructure, like sitting on AWS Bedrock. We can also validate your AI application, which is already integrated with different models, or maybe your in-house model, right? Those applications could be on the public cloud, or it could be on your private cloud as well. So after defining the application type, we will start validating that application by launching a series of attacks. Basically, more than 2,000 prompt messages. So let me show an example of one of the validation exercise I have already done on my application, which is basically using Gemini. In that particular application, you can see it is hosted in my lab environment with this API. I can see summary out of all the attacks or prompt messages, 83% of those prompt messages were blocked by built-in security of Gemini, which is good, quite decent, right? But still, 17% of the attacks went through. So let me show you how it looked like. So when I click here, you can see the summary of all the prompt messages which we have sent by this platform. So in my example, 83% were blocked, which means in this case, I launched only 200, roughly 200. Actually, we can do more than 2,000, but I hit the free limit of my Gemini account, so I have to stop my validation. So I can see 35 were successful. I can find out more details about the attacks that went successful. So by playing around with the filters. So these are the attacks that went through. If I click, so you can see the mapping of these attacks against the techniques and tactics defined by MITRE or OWASP. If I click there, I can actually see the prompt messages which we have sent to that application and the respond to that prompt message as well. So complete details will be visible. Once we perform the validation, it's now time to enforce security guardrails. See, for any foundation model, for sure there will be weaknesses. But the idea here is not to discourage to you stop using those foundation models. Instead, we want to show you what are the risks associated with that and how you can secure or address those risks with the help of runtime protection, which we can enforce with the help of AI guardrails. So let me show an example how we can enforce those guardrails. So I define the policy name test to, let's say, so we can do this enforcement using multiple methods. Again, it depends where the application is hosted. So we can put a security gateway that will sit in line between the users and the application, or we can basically leverage API endpoint that can reach any type of application. So after specifying the deployment method, I pick the application, my lab application, and then I define which type of AI guardrails I want to enforce. So three categories of guardrails: security, privacy, and safety. Inside security, I have prompt injection, code detection. I have separate guardrails for privacy, where I have different type of classifiers like email address, IP address, PII details, right? And then safety guardrails. After doing few clicks, the policy will be enforced either on the security gateway or via the API endpoint. So once we enforce the policies, whenever we receive a prompt message that violate these security policies, we are going to block and report it here. So in this example, I can see this was a prompt message sent by me, which was blocked by AI Defense. let me show you a live example. So earlier, I demonstrated that how we can use these prompt techniques to bypass the built-in security. But after we secure the application, the built-in guardrail is going to protect it. So you can see your request violates the policies enforced by your organization. That's why it gets blocked. Just to give you an understanding of what's happening behind the scenes, so I have logged into my test environment. I'm using N8N platform. It is basically an AI studio that helps you to define different type of AI workflows or AI automation tasks. So in this particular environment, I have in the middle AI agent that is connected to my Gemini model. This platform also offers a chat interface. In the middle, I have inserted AI defense. So whenever I send any message, let's say first the message will be validated by AI defense. If the message is allowed not by the corporate policy, it will then process by your AI agent. After that, the response part will also further get evaluated by the AI defense itself. And if we find the response is not violating your policy, then it will receive back. Here you can see I got the response that how I can help you. So I'm going to copy and paste the same prompt message just to demonstrate what's happening behind the scenes. So when I try to insert the same prompt message, it was blocked by AI defense straight away. The message was never processed by the AI agent. So this was about securing your in-house AI application. How about how we can control and secure the usage of different Gen AI applications over internet? As I said, to cover all type of users, we are leveraging our SSE solution, which we call Cisco Secure Access. So within the Secure Access, we have infused the AI defense capability to address the use case of that third-party AI access. Good news is that within the same platform, we can manage the security policies of Secure Access. So just to show you a quick demonstration on how we are controlling it, I have logged into Secure Access. Basically, we are leveraging data loss prevention policy. Within the data loss prevention policy, we use multiple techniques, combination of multiple techniques, like traditional DLP and AI guardrails. In the traditional DLP, we primarily use basically regular expression to match different type of data. Things like, let's say, if you provide credit card details, right? There is already built-in regular expressions available to match the prompt message against credit card details, against date of birth, against bank account number, against license number, right? So that's a basic method, right? I would say a first line of defense. Let's say after that, all the low-hanging fruits will be cut down by this technique, and then we will start using AI guardrail. So with the help of AI guardrail, we try to understand the intent of the conversation. So whatever you write in the prompt message, we try to understand the context, the intent, and if we find the intent is violating your uh, policies, we are going to block it. So just to showcase how it looks like, so I'm trying to take a policy, first the basic DLP policy, and then the AI guardrail rule. So I name the policy here. I can specify what type of data classification I want to use. So you can see we already got built-in data classification available for different type of compliances like GDPR, HIPAA, PCI, and you can also introduce your customized data classifiers here. You can enforce this policy to one user, to a one branch, to complete organization, or to some group of users, right? By picking up those identities here. You can enforce that DLP across all the websites over internet, or you can pick and choose some categories of website. In my case, I want to enforce that for different Gen AI applications, right? So I selected generative AI. You can see we can actually control the usage of more than 1,300 Gen AI applications over internet, which is very huge. After selecting those and doing few clicks, the policy will be ready. That was traditional data loss prevention, right? How about enforcing AI security guardrails that can understand the intent of the conversation? So when I go there, I specify the rule name, I specify what type of guardrails I want to enforce, security, privacy, and safety. Then again, I specify the identity and the category of model. So here we are defining what type of model you want to control, right? So you can see DeepSeek. So in this next demo, we are going to showcase quickly how we are controlling DeepSeek as an example. So we can control the prompt part, the response part, or both directions. And after doing few clicks, the policy will be ready. So coming back to the last demo, before we wrap up, this is Gemini, right? Also a DeepSeek. We asked DeepSeek to write a professional email about some financial records. It is going to be blocked because of the security policy I have defined inside AI Defense. In second prompt, we attach a file that contains sensitive data. So we can read those data and we can block the message here. So we try to attach the file here. Again, it will be blocked. Then in the last, we use prompt injection technique to trick the chatbot. But again, it is going to be blocked straight away. So here, I put the prompt message and it was blocked. So that was the last demo, and it is a wrap. So there are some resources which you can navigate later on from our website. The slide pack will be available for you to consume once you finish the survey part. And the session is getting recorded as well. You will find inside the Cisco U YouTube channel. And please complete your surveys. Your surveys are very critical for us. So once again, thank you for your time and thanks for joining me. Thank you.